Great. So welcome back, everybody. This is V.S. Subramanian again from Dartmouth College, and I'm pleased to welcome you to day 2 of the joint course being offered by the Institute for Security, Technology, and Society at Dartmouth, of course, being delivered by folks at Google. And today we'll be talking about exploring a host of different Android malware techniques. And the agenda for the day is shown on this chart. So we will have 3 lectures this morning, starting with JJ, who'll get started with hybrid Android apps and malware based on WebView and JavaScript. We'll have a lecture by Arthur Kaiser on cloaking, full fraud by Vadim. And then we'll take a sort of a West Coast lunch break, get everybody a chance to, just chill for a little bit. And then we'll come back at 4 o'clock for ad fraud by Arthur, and then JNI and analysis with Gidra by Vadim, followed by a lab. Again, I would encourage all participants to be active and ask questions and make this interactive, but again, subject to the idea that our friend, because of the remote nature of this, our friends from Google will speak independently for about 45 minutes for each hour session, and then 45-50 minutes, and then we'll have some quick overview of the session. But feel free to send questions in by chat throughout the session. We will read them out at the end. So you don't have to wait till the end to ask questions. Just you have to wait till the end to ask questions verbally. Okay? By the way, talking of which, Bill, I'm not seeing the chat icon in my screen. Oh, I do. Okay, thanks. Okay, and so our speakers today are JJ Arshad, who's a security software engineer in the Android security and privacy team at Google. He's been working in security issues for several years. After that, Arthur Kaiser, who's been looking at a variety of online abuse, researching unwanted code on people's machines.
Yeah, I was on the Skype call. I was about to.
And then Vadim Kotov, who's a security engineer, who basically looks at unpacking Android malware. And he'll be speaking to us also later today. Again, this is sort of just as much a legal note as something we want you to be aware of. The entire course is being recorded, and we'll eventually make it available to at least participants from here. I do want to remind everybody to please turn off their mics once the session starts. So with that, I'll stop sharing and welcome JJ to talk to us about malware attacks that leverage web views. Thank you, and over to you, JJ.
Thank you. Let me share my screen. So can you all see it?
Yeah. Yes, thanks.
All right. Oops. Why did I click on share? So, hello everyone. It's nice to being back. Can everyone hear me very clearly without breaking up?
Yes.
Okay,
yes.
Great. All right. So today we're going to talk about the hybrid Android apps, the era of WebView and the JavaScript. So as you know, yesterday we talked about like different techniques that we can write apps either using Java or developing native apps, and I talked a little bit about the hybrid apps that you can use, like HTML and JavaScript to integrate web content. So the agenda today is to introduce the hybrid apps, talk about the WebView APIs and some samples, and then we talk about the potentially harmful applications that Sebastian introduced yesterday in the first session. And we're going to go over some PHA samples and potential techniques that can be used by PHA applications to somehow erase the user data and the device. So as we know, the apps usually were developed using like specific platform language and SDK. For example, we use Java or Kotlin for Android, or we use the Objective-C for the iOS. But the hybrid apps allow us to integrate the web content using some kind of embedded browser in the app, which is the WebView in the case of the Android, or UI WebView in the case of the iOS. And you can basically write any web content using the HTML, JavaScript, and CSS. And the interesting part is that the Android allows you to basically have a nice communication and collaboration between the web content loaded in the WebView and the rest of the app, which is written in Java. In order to do that, as we talked yesterday, there is the Java API framework that provides a huge set of APIs for the apps to work with. One of those APIs are WebView APIs, which basically there is a tremendous amount of like APIs that allow the app to do any, like most of the stuff that is necessary to be done. For example, they can load web pages, they can visit sites, they can execute JavaScript. And this integration is so coupled that the Java code somehow can meddle with the content loaded in the WebView. So there is no very strong isolation between the Java and the JavaScript. For example, the Java code can manipulate the DOM by injecting the JavaScripts. It can read the cookies. It can override like all sort of URL loading behaviors by implementing some callbacks, or even intervene with the UI dialogues with different methods and functions that are there, such as like accepting alert or accepting confirm or this kind of things. So there are a couple of classes that provide that functionality. The main one is the WebView, which is the main class that you basically create and you work with it. So as you can see, there is a lot of APIs here for loading a URL, posting content to a remote website, loading data, like inline data, even you can run JavaScript, like using the established JavaScript. You can send a message using the post message. And some interesting thing that we're gonna go deeper in future slides is the JavaScript interfaces, AKA JavaScript bridges, which basically allows the JavaScript code to call some Java code from inside the WebView, which is like interesting and dangerous sometimes. There are other classes about like web messaging. As you know, the JavaScript interface has been around for a long time. And basically what happened was that there was a lot of vulnerabilities, a lot of problems. That's why the Android started introducing new web APIs. The main one is like post message, that we've seen the equivalent in the web environment HTML5, that they try to encourage the developers, instead of like doing direct function calls or direct method invocations, they use the messaging APIs, so for a safer and less vulnerable code. And they're planning to discontinue the JavaScript interfaces as soon as the post message has been used. We looked at a lot of applications in Google, and we've seen like many apps already adopted this technique, and it basically removed many of the vulnerabilities that are known to the JavaScript interfaces. So I'll just provide very, very quick samples, like how exactly it works, like how the API is supposed to be called. The main one was the load URL and the post URL. And load URL is basically loading some some remote website. It could be even a local website. And for the post URL, you can technically submit something to the website. For the loading local files, as you know, as we talked about yesterday, the APK can be packaged with some asset file or resource file. One of the main ones are the assets that is in the assets folder, and you can put in all sort of JavaScript, HTML, or any kind of file. And this is the way that you can access those files using the file scheme and Android asset as a probably host name. And from there, you can add the path and you can access any arbitrary file inside your assets folder. That we talk about it later, that how that could be interesting, or we can talk about it now. I mean, in some cases, such as phishing, sometimes some apps package the phishing page with them, and they load it like locally instead of like loading, for example, Facebook from the Facebook remote website. They're gonna load a page locally from their assets file, which looks like the web Facebook, and they try to convince the users to enter the username and password, and then hijack the password. So it's really important to look at those files as well to see what they're up to. All right. Cool. So another thing is loading inline content. So the inline content is any kind of like inline Javas, inline HTML that can also be loaded into the WebView. And the interesting point about the inline HTML is that no network request is gonna go out of the Android, the Android device or the app. And sometimes it could be helpful for the malware or show that they are contacting some remote contents, so they can basically load the HTML content like locally, which is embedded in source code and work. As you can see here, the like our data URL to load some inline content. The main one is like put the HTML into the URL itself and load by using any kind of the load URL, the post URL, or even encoding base64 and load that encoded URL, which is quite like a standard way to load the URLs. So one more thing is that another way for loading inline HTML, there are like some APIs such as load data and load. You can immediately load some content that you want into the WebView, both as a like regular HTML or either as a encoded base64 encoded content. Even more crazier than that, you can execute like JavaScript like right away into the WebView using the JavaScript colon type of a scheme. This is something only in the WebView. As I know, this is not a valid JavaScript. in the regular web, and it's only known to the WebView. That you can use the load URL and post URL immediately by prepending the JavaScript with the JavaScript calling string. In order to discourage that WebView introduced another API called the Evaluate JavaScript that you can easily use to, run your JavaScript without like putting anything in front of it. And the second argument, which I passed the null here right now, is like it could be some kind of callback. You can get the results back that we show later how it can be used. So another thing that I talked about was the JavaScript interfaces or JavaScript bridges. That was the initial way that was introduced by Android for the Java and the JavaScript code talk to each other. So the way it works is that you create a class inside your Java, let's say JS object, and you create some methods that you want to be called by the JavaScript, and you have to add this JavaScript interface annotations. A long time ago, there was no annotation. All the functions in the object could be called, but because of some vulnerabilities it introduced, the developer has to annotate all the methods that needs to be called explicitly. And in the second line, you do the add JavaScript interface. What you do, you create an object and assign a alias to it or name to it. And you inject this JavaScript into the WebView. As you can see, the JS underscore object, it's being added to the variable, the global variable scope of the JavaScript. And the JavaScript can behave with it as it is some normal object and call the functions, which is here the JS object.method. And as you can see, it's going to return this is Java. This is Java is syntactically incorrect. I had to add a double quote, sorry for that. But the thing is that this is a very cool way to call the methods of the Java, but sometimes it could be complicated. What if the return type is not some primitive type, or it's not a known type, such as a string? It could be some other objects that bring more complications that I'm not gonna go through with. But as you know, the JavaScript interface could be quite complex. As we talked, the messaging API was introduced to Java, to WebView, to be used by the JavaScript. The simple version is the post web message, which is what happens is that in the post message, you create a web message and you have to provide the URL of the WebView, which is basically the origin of that WebView, to make sure that we are posting the message to the right origin. And on the JavaScript part, you basically have this JavaScript has to implement a onMessage callback. And when it receives a message, it's going to be called with the E event, which contains the data. And as you can see, it says, I am Java here. So this is a one directional messaging from the Java to JavaScript. In order to make it even more interesting, they created a bi-directional way for the Java and JavaScript to talk to each other. And it's quite similar to the ones that we see for the HTML5, how two JavaScript can, across two frames, can talk to each other. So simply what happens is that in the JavaScript, you have to have the onMessage callback being defined. And in the onMessage callback, you receive some kind of event that has some kind of data in it. And more interestingly, it has a channel in it that is provided by the ports. It's like a pipe channel that one side is the JavaScript and the other side is the Java. And using this port, you can develop the unmessage on top of it, and you can start talking. So you can say post message, and on the Java side, first of all, you have to send the web message to want to talk and create the channel that I talked about that basically and send this origin. And on the Java side as well, you can listen to messages using implementing the web message callback. That if you implement the onMessage method, you can receive all sort of messages that is coming back from the JavaScript. And using the port here, you can like send more messages. So it creates some kind of, bi-directional channel between the JavaScript and the Java. So I talked about all those to get to the fact that the PHAs that we talked about yesterday in Sebastian's session are basically the apps that can put the users and user data at risk. And we usually call them like malware, but not all of them are malware. The main ones are backdoor, toll fraud, like phishing. And we have another category, which is called like the mobile unwanted software, or the MUS, which aren't strictly malware, but could be harmful, such as like ad fraud and click fraud. So the reason I talked about the hybrid app was that some of these malwares and the MUS categories for the apps are heavily use the JavaScript or partially use the JavaScript at the WebView for launching their attacks. I mean, some categories may not need the WebView at all, so they can do everything in the Java or in the native part of the code for more obfuscation. But some categories more or less needs the WebView and the JavaScript to launch their attack. And three of the categories that are like this are ad fraud or click fraud, toll fraud, and the phishing. So I'm going to go over these three very quickly, provide some samples, but my colleagues are going to talk in more detail about every one of these attacks in future sessions. So definitely attend those to know how exactly in detail they are working, and they're going to go through some real malwares and show you how this communication and interaction happens. So in case of the ad fraud, basically the apps that generate like ad interactions to trick, an ad network into believing that the traffic is authentic or coming from some real users. But as you know, it's an invalid traffic, and it's putting a lot of damages, to financial damages to the advertiser and the ad networks. And some of the ways to like show hidden ads to get impression, automatically clicking ads to get get money for every click that they're doing, or even use bots for doing this. Click fraud apps are some specific type of ad fraud, which is basically they load pages with advertisement in them and automatically click on them without the user intention. One of the samples that we found in the wild was this. It does basically is that the app load the web page into the WebView and then inject this JavaScript using either the evaluate JavaScript or the load URL API. And what it does is that, as you can see, it grabs all the A links, A elements, which is all the links, and it put all of them in the array, randomly choose one of them and click on that specific link. And they're doing this over and over again. So to make it, a little bit random, to make sure that on the server side, nobody understands this is a click fraud, but at the same time, they are generating revenue. Because many of the apps nowadays. This is their main source of income. They are being freely available to the people, but this is how they make money, by showing advertisement. But at the same time, they do this kind of fraud in order to make it, to make more money, basically. So in the toll fraud case, there are the apps that trick users into subscribing or purchasing content via their mobile phone. And some of cases are direct carrier billing or wireless application protocol. The app fraud is kind of one of the most prevalent types of toll fraud, and they somehow trick users to click on a button, or they use a JavaScript to load the web page, fill out the form, and click. And this causes some for the website to send some SMS for confirmation or maybe email, and those apps also, try to hijack those SMS or email in order for the users to understand or to know what happened. And a lot of the toll fraud functionality is being implemented on the Java side, and it has a very small JavaScript part that we're going to talk about here. So it could be as simple as this. It's just simply fill out the form with some value and then click on the button. So this way, there's going to be some HTTP request initiated to the website, and the website thing is coming from the user, and it takes out some money from the user's account. So the phishing. Phishing apps usually pretend to come from some trustworthy sources and try to somehow leak the PII through the remote website or their third party. This PII could be like banking credentials, so this is a very huge category, and it applies to the code that intercepts the transmission of user credential in transit. So focus is mostly on the apps that are utilizing the WebView and JavaScript. There is going to be another session on that talk in detail about how different types of phishing are working. Like some samples are real, and some samples could be potentially can be used by the malware apps. So the very first one, as we talk, JavaScript can call some Java code. So the whole thread model here is that the app load the web page into the WebView. The user start filling out some sensitive information. Click on the submit button or did some other actions. This information is going to be collected by the JavaScript that was injected to the page and being sent somewhere. In this case, and in a case on the JavaScript, but sometimes it can be leaked directly outside to the network by initiating some HTTP requests. So in this case, the JavaScript is sending a username and password. In this case, it was a Instagram page. And as you can see, when the user click on the submit button, this JavaScript, like looking at this unclick event, and as soon as it was collected, it's going to collect the username and password, can put this information with some other information and send it to the server. Another technique is result callback. As we talked earlier, there was a new JavaScript API called Evaluate JavaScript. What it does is that it injects some script to the page and listen on the result of the JavaScript. So the result in JavaScript is that this is another interesting concept in the Android, that the JavaScript data can be returned back to the Java side using the evaluate JavaScript. What happens here is that, as you can see, there was a sample that collect the username and password and return from the function, and the whole function is being called. So what happens here is that when is the last expression that was called. And what the WebView does, it sends the value through this callback, which is called the value callback on the receive value. And for the JavaScript, this is another API was introduced to deprecate the JavaScript interface, to give the application in a way to collect some value from the JavaScript and the WebView, which is being used regularly. I've seen leaking the information through some of the UI elements. And as you can see here, the attacker or the malware is collecting some information and look at the click event, collect the password, collect the username, and put all this together and eventually call the alert and confirm API. The alert and confirm API are the ones that allow you to show some dialogue in the JavaScript. Alert is just show information, like confirm, you can put the yes or no. And what happens on the Java side is that there is a class called the Web Chrome client, which is responsible for handling UI interaction with the WebView. And as you can see, two of the most interesting callbacks are onJS alert and onJS confirm. What happens was that here, the attacker or the malware put the information into the this string, the row 1 and row 2, and call the alert on it. And here you see the string message contains the username and password. And this is how the malware could leak the information from inside the JavaScript to the Java. So this is not a normal way to do it, but that's how they did it, and it seems quite elegant. So this was all about leaking information from JavaScript to the Java side. I went a step further because I'm mostly working on phishing malwares at Google. That's why I started instead of reacting to the way and finding new samples that are doing something, I started thinking, what are the other ways that the malware can leak the information to the outside? So from here forward, these are not real samples. These are the samples I came up with, the scenarios that the malwares can use to leak the information. So one of the ways is, instead of sending that JavaScript to the Java side, I said, okay, how about JavaScript sending information directly to the outside, to the remote website? The techniques that is more or less more frequently being used in the normal web, in the desktop like browsers, because there's no the Java side there, so they have to communicate with the remote server. That's why not they can do it here. So one of the ways is to creating some network requests and put the information inside the network request. One of the API is fetch, which is, as you can see here, we can get the password. You can fetch a URL and put the password somehow into the URL. So this is a very abstract way of showing this. Otherwise, the password could have space, non-URL friendly characters. So the malware should somehow encode the password into the URL to make it URL friendly. But for the sake of the argument, we're going to say it's going to happen this way. So as you can see here, the fetch is going to create some remote. It's going to create a HTTP GET request and send all this information to the server side, and the server side can get the password. Even with fetch, you can post stuff instead of going through all the encoding the password to the URL. You can simply connect to the malware side and use the post method, and in the body put the password, which is quite nicer. Another way is using the request and fetch again. You get the password, you create a request class, put the password into the get URL and fetch the request. Or you can create a request with the website, with the method post, and input the body, and then fetch the post request. Another way is which is being used a lot of time. In the JavaScript, you can create HTML requests, set some headers, and even you can password in the header. Or you can put the password into the get URL and send the XHR. Or you can post the information using the XHR post and then send the information using the send API as be shown here. Another way is the WebSocket. You can either use the password into the URL and the WSS, which is equivalent to the HTTPS. Or the normal way is to connect to the website and use the send API to send the password. It can get even more crazier using the DOM manipulation. Actually, this DOM manipulation technique is being used by many websites, some trackers or advertisers, that they indirectly create some HTTP requests, mostly GET. What they do is that they create some element dynamically, maybe an image or an iframe, and inject or add that element to the DOM. What happens is that the browser understand this and try to load that element from the remote website, if it's an iframe or maybe image or JavaScript. And this is the way they can leak the information, and it's being used already by trackers. You've probably seen in your browser, you have a lot of like 1x1 pixel, 1x1 images that are injected into your DOM, and they have a very weird looking long, URL. So what they do is that they put a bunch of information there and they inject the image to the DOM. So the user cannot see it, but the remote website can grab the URL and extract the information. So one of the very main ones are the create elements or the create element NS. So what happens here is that use the create element, use a tag name, set the source, encode the password to the URL and append it to the body. It's going to create a request to this URL. There are other ways for doing this, like create element ns or even create element and use the set attribute on the source with the URL. Or you can use like properties such as outer HTML that you build the URL yourself and put it into the outer HTML. Or create a div element and use the inner HTML to put the information in it. There are more other ways for doing that, like using the href for the link or the data attribute for the object element. As you can see here, you can create attribute, you can put the information into the value, and then you can set the attribute. So as you can see, there are so many ways and techniques that we can use for achieving this purpose. Or instead of like creating new elements, the JavaScript is able to change the existing elements. For example, they can change the source of the current frames. So when you do this, what happens is that the browser or the WebView immediately generates some HTTP request to grab the content, and the information will be leaked. Or even get the element, use the set attribute, or even get the element and use the outer HTML to replace the current HTML. We can use the same thing for the inner HTML, replace the value, or get the attribute node API to get the source, the current version of the source, and change the value. Another way is to open new window. As you can see here, you can use the window open or document open to put the password into the URL and leak the information. Or either you can grab this information from the server side, or you can use the WebView.get URL to retrieve the current URL, or even use the other like callbacks, such as the should override URL loading to grab the loaded URL on the Java side to extract the information. Another way is using the location, window location. There are different ways that you can put the password into the URL in order to leak it somehow. And you can use the same techniques as before to extract the URL on the Java side. That's the same thing for the document location, pretty much the same. Another way is like setting the title of the WebView. The WebView, even though you cannot see the title, you can set the title and put the password into the title, and later on call the WebView.get title, to retrieve the password on the Java side. And finally, even you can play with the cookies, put the password into the cookies, and later on use the cookie manager API to get the cookie from that web URL. Or this is the practice that is being used for advertising, that you can put the cookie somehow into the cookie jar, and it's going to be sent eventually to some third party when future request happens. That's another way to leak the information. So this is all the techniques that we basically could be using for doing phishing. The reason I learned that more phishing was that like phishing is one of the categories is heavily relying on the JavaScript and the WebView to implement their techniques and leak information and steal information. But definitely to learn more about the other techniques in the phishing or the ad fraud and the toll fraud and what happens on the Java side, because this is a collaboration between Java and the JavaScript and the WebView. And when we put all this together, the malware eventually can do their thing. So I hope it was useful, and I'm happy to get any questions.
Thank you, JJ. This was incredibly valuable. So let me throw open the floor for questions. I did see some stuff fly around in chat as well, which seems to have been answered by one of the other participants, but you may want to chime in on that as well. So, but folks, please feel free to ask questions.
Yeah, thank you, JJ. For what it's worth, I cannot overstate just how important this topic is, because there's a lot of malware that is moving into the JavaScript space. And so having an understanding of what to look for is not just important for like manual analysis, but also if you want to do at-scale analysis, either static or dynamic. So it's becoming increasingly relevant.
Yeah.
You know, I had a quick question on that, which is, are you, what do you see as the increased trajectory in terms of, you know, use of JavaScript to carry out such attacks?
Sebastian, do you want to?
Increasing in the next few years, or do you think it's plateaued?
There's a couple of very lucrative kinds of malware like click fraud that are very easy to execute in JavaScript.
Mm-hmm.
So I think it'll become more important, even more important than it is right now. I think it has.
Got it.
I had a question.
Sure.
Samid, go ahead.
I was wondering if you've looked at like sanitizing the input language, or like sanitizing the input that goes between Java and JavaScript to ensure that only a restricted subset of JavaScript can maybe go through, and that can somehow prevent these kind of attacks on the on the consumers.
So one thing is that we have like two different threat models here, right? So there are a lot of like papers out there talking about the vulnerabilities in the WebView. So the assumption is that over there, we have some benign apps that somehow being compromised, or they're being misused, and some malicious JavaScript is gonna come in and misuse those apps. But in this case, like we're dealing with malware apps, and they are handling everything from end to end. So the Java side is malware, the JavaScript part is malware, the native part is malware. So basically, the Java knows that what is injecting to the WebView and what kind of content is loading in order to launch the attack. So it's not kind of, I guess, quite, maybe somebody can implement some techniques in lower levels, maybe in the WebView level, in order to, you know, somehow like prevent this type of things. But for now, I think because the malware is like responsible for all of it, I'm not sure like sanitization is something that we can like consider. I'm not sure if I understood the question quite correctly.
That's great. Yeah, that answered my question. Thank you.
Sure.
Thank you, Samid.
So I had a question, and
Sure.
I was wondering about, so some of the examples that you showed towards the end, I think, where they had like WebSockets and stuff to actually communicate the password to the attacker.
Yeah.
Those sort of techniques are something that you would even see in benign apps, right? Like, so I can write an app and submit it to the App Store that may also have a technique where there is some data on the phone that I'm continuously relaying via WebSocket. So I was sort of wondering, of the apps that are submitted to the App Store, how do you, is there any automated way that you have to test which sort of patterns are benign and which sort of patterns are could be phishing attacks?
Mm-hmm. So that's a very interesting question. So that's why I talk about the big picture that knows what the app is doing in all three parts, the Java native and the JavaScript. So in our part in the JavaScript, the only thing that we're doing is that we're generating some intels that this JavaScript is issuing some WebSocket that is leaking some information in the DOM, right? It could be malicious or it could be benign. We add this intel to other intel we gather from the Java and the native. And when we put all of this together, we can say if the app was doing something malicious or not. So these techniques that I showed here, that could be used by the benign apps, but either of them are not indicative of any malicious behavior by themselves individually. But when you put all of this information together, all the intels from the all parts of the app as a whole, you probably can say, okay, I collected like 10 evidence that these behaviors are happening, and there is no way that all of these 10 should be happening together. And that's how we detect the malwares. But for sure, sometimes there's always like false positives. There might be some apps that doing this that we should consider as a false positives.
Thank you. Yeah.
Excellent. Thanks, Prashant. Any more questions? Okay, awesome. So again, thank you, JJ. Again, great and very insightful presentation. So we will do a little thing. As we are actually on time today compared to yesterday, we will take a, let's say it's 12:56 according to my clock. Let's say take a 5-6 minute break and come back shortly after 1 p.m. Eastern and listen to Arthur's talk on cloaking. So again, 5-minute break approximately. So we'll come back just after 1 o'clock. Okay, welcome back everybody. And we're now ready to listen to Arthur's tutorial on cloaking techniques. So over to you, Arthur.
Thank you so much. I'm glad to be with you all today, and hopefully this will be a very informative session. I think this will probably go a little shorter than planned, and that should give us quite a bit of time for questions, which I expect there'll probably be some. So let's go ahead and get started. Everything technically is working okay so far. You guys can hear me okay, and the slides are working?
Looks good, Arthur.
Thank you so much. All right, so cloaking techniques. This is one of my favorite topics. I find it very interesting because it has some very technical aspects, but also kind of focuses on the operational side of malware distribution and effective malware campaigns, as well as adware. Okay, so let's get started. So to define cloaking, what we're really talking about here is detection evasion. And I define cloaking as ensuring that certain behaviors that exist within your app are going to only trigger when specified conditions are met. And otherwise, those conditions are not going to trigger. So this allows you to hide from analysts and is extremely essential to the success of your malicious campaign. The most impactful malware and fraud campaigns are highly organized and are operated very much like a business. So in order to succeed in that endeavor, you really need to be able to hide from defenders of the ecosystem like us at Google, or third-party antivirus vendors, or academic researchers who may publish information about your fraud. But you also, in order to generate far-reaching campaigns, you need to fool other people as well, because you're probably going to have partners that are involved in your campaign that are probably unwilling. So if you were around for Sebastian's talk yesterday, he had mentioned that there's quite a bit of pre-installed malware. The manufacturers of these phones and the creators of these build images, they aren't trying to put malware on their phones. In fact, most of the time they're deceived by some third-party vendor that's part of their campaign. And the way that they're deceived is that the malicious actor has hidden their functionality so that when they test their apps, it looks fine. But once it goes out into the wild, things change quite a bit. And aside from profiling the device and not executing under certain conditions, you can also take a more brute force approach and really just delay your functionality over a period of time. And this is going to prevent sandboxes from seeing things because they're only going to run for a few minutes, maybe a couple hours even. And analysts too aren't going to spend, for most part, many days looking at your app, right? So if you can wait 3 or 4 days after the app is installed before you do your malicious functionality, you're gonna have a much better success rate in not getting caught. So this also has other benefits as well. For example, if you're an aggressive adware or click fraud campaign and you're doing lots of pop-ups and creating annoying or disruptive advertising, if you wait a few days, the chances are the user's not going to remember which app people install different apps each day. And if you just start popping up out of random, 3 days later, it's much less likely that the user who just installed your app is going to remember that your flashlight app is the one that's causing these disruptive ads, right? It's going to be very hard to tell which one's doing it if it was 3 days ago when you installed the app. So I see this very, very often where threat actors have a long delay, and we see it in code, and also they can set the server side where they will record your install time, and then they'll target you based on that install time at a future date. Okay, so we kind of discussed why it's very important for threat actors to know about cloaking and to implement it well, but we also need, as researchers and defenders, to understand this concept because it can affect our data analysis, it can affect our gathering of data and our reports on the data that we find. So if you're gathering say dynamic analysis data from a virtual environment, and you have no comparison to like a physical phone, chances are you're probably missing quite a bit. Most malware nowadays is a virtual device aware, and that's actually across all platforms, iOS, Windows, Android. So you want to at least do some kind of sanity check with a physical device in the malware that you're analyzing. Additionally, most malware, and particularly advertising fraud, they are buying their users from some type of app distribution channel. So they track these paid for installs at a quite granular level. So if you just install, say, a sample from VirusTotal or like some kind of malware store that's intended for research purposes, you're very likely to get a much different experience than what you would find by installing from an in the wild source, like by clicking on an ad or clicking on a Facebook link or Twitter link or something like that. And the way they make this different, they make the difference between these two installs is that a referrer is sent up to their servers or to a third-party tracking service when you make the installation. So by having a null referrer, you're basically telling the malware author, like, hey, you didn't pay for me, so don't risk showing me what you don't want me to see because I'm not a paid-for user, so there's no loss there. And like I mentioned before, bad actors are expecting analysts and researchers not to spend a long time on an individual app. In fact, that's just not really scalable. So the best thing they can do is just wait you out. So if you are doing some kind of deep dive into a specific threat actor, I do strongly recommend that you create an installation that you can let sit for a long period of time and see if that's why you're missing the bad behavior. And so this is something I've been studying. I've been in the ad tech industry for about 10 years now, and I've been studying these type of cloaking behaviors during that time across all platforms. And I found that there's just some universal tactics and procedures that we see across all malicious campaigns. And they basically boil down to this. You need to set up some kind of command and control infrastructure to ensure that you can remotely tell your app what to do and when to do it. And you're going to start communicating with the infrastructure by gathering client-side data at the time of install. So I'm going to fingerprint the device at the time of install, and I'm going to try to use some kind of persistent feature that's going to ensure that if you install my app multiple times, I'm going to be able to get the same fingerprint for you each time. And the way that this is generally done is by finding some specific hardware identifier, maybe a serial number or an Android ID or MAC address that's not very mutable. So you're going to find some persistent feature and you're going to send that up to fingerprint that user, which then you're going to store somewhere in like a Hadoop cluster or some kind of relational database to tell you, like, I'm going to be able to target this user at a specific time. I may be able to turn off and on malicious features against that user. And in addition to having this persistent ID, you're also going to want a unique, so you have this unique device identifier, but you also are going to want a one-time install token. And this allows you to blocklist users who are installing you too frequently. A legitimate user who you're trying to scam isn't going to install your app 18 times. An analyst or a sandbox probably will. So if I have these two signatures, I have your device and I keep seeing that your device has all these install tokens, I can actually just set up automation that says, well, every persistent ID that installs more than 4 times in a 24-hour period is a potential analyst, and I'm not going to target them with whatever behavior I'm going to see. And I've seen that done on Windows, on Android, on Mac OS. It's very common. Aside from the device-specific info that you're collecting, you also want to ensure that the web requests you're receiving from your client are not from, say, an ASN owned by Google or Amazon or Microsoft or a common cloud provider. Many VPN providers have no net blocks that are associated with them that are only used for proxying or VPN, so you may block those. Additionally, many of the antivirus vendors have registered net blocks, and you can see that you know, your installs came from McAfee or ESET, and so you're going to behave much differently when you know, McAfee or Trend Micro installs your app first when a normal user installs your app. So you need to have a complex server-side system that ensures that you can basically pull levers on your app and make real-time or long-term decisions based on the data that you're collecting from the device. And all of these aspects together are really what cloaking is. The individual techniques, and we're going to talk about those more later, are really those vary quite a bit, but these kind of core concepts, these have been here and haven't really changed at all. Okay. So you may be thinking to yourself, well, here's a lot of things like detecting virtualized devices. Why don't we just create policies or just start blocking all the apps that detect whether you're running in a virtualized device? And well, we'd probably like to do that, and it could make our life easier. There's many legitimate reasons for doing these type of activities that aren't nefarious. So for example, I may be an advertising SDK, and I may also check if I'm a virtualized device and change my behavior because of virtualized device, but it's because I find that virtualized devices are almost always used for fraud and never for real users, so I'm just not going to show ads in virtualized device. Well, this is not a malicious action. In fact, it's protecting the advertisers from excessive fraud. So it's something we want to encourage. So there's a high crossover between anti-fraud techniques and nefarious cloaking techniques. And this makes it very difficult for us to kind of structure detection solely based on cloaking. Generally, cloaking is like an indicator that is part of a more accurate badness review. So another thing I've been seeing that's becoming more common more recently is using third-party attribution companies or campaign tracking companies. This is software that you basically purchase an API token for that allows you to track installs of your app. It helps you, track advertising campaigns. You've all definitely seen an ad to install an app. Those ads are quite expensive, and the people who are running them want to make sure that they are getting the installs that they're targeting. So there's a lot of software that allows you to track and install very carefully, and that can be used for the purpose of ensuring that you're not installing on an analyst or a partner phone or something that you don't want someone to see. Additionally, a lot of the system information that we would use for cloaking heuristics, checking CPU type, checking the brand of the phone, these are things that bad actors like to do, but they're also very important for like games that may require a certain level of CPU or chipset, and may only work on certain phone brands or screens. So it becomes very difficult for us to create heuristics that say, well, this is checking for this CPU type, therefore it must be doing some kind of malicious cloaking. Well, there's quite a few legitimate reasons to be doing this. All right. Additionally, you may see actually legitimate behavior changes based on network requests, and these can be because of promotions that are specific to certain countries or certain locations. And again, this is completely legitimate functionality, but it has a high crossover with malicious functionality. Okay, so I had mentioned this before, and I kind of wanted to reiterate what's going on for a lot of both malware and ad fraud campaigns. They are actually not getting installs just by people going to the store and searching for their app and downloading it. They're usually getting these installs through some type of promotion, and that's usually paid for advertising or some kind of viral marketing campaign, some kind of gimmick in order to get people to get clicks. And these campaigns are well tracked both by third-party tools and through DIY refers tracking systems. So when I buy installs, these are the users where I'm trying to make a return on investment for these purchases, right? It could cost me $1 for you to click on my ad, and I want to try to make $1.10 off of you in order to keep myself in business. And I'm probably going to make that $1.10 for our purposes by doing some kind of fraud, or by maybe signing you up for a subscription you don't want or something like that. So one of the most common cloaking techniques I see, and one of the hardest for us to get around, is bad actors just choosing, if I didn't pay for you, you're only going to get the advertised functionality of my app. And this makes it very hard for our systems to detect the bad functionality, but it also makes it so they are ensuring that their risk has been minimized. I don't need to make money off you if I got your install for free. If you happen to install my flashlight or compass app just by an organic search on the Play Store, I don't really care about you. You're in this bucket of organic or a quality assurance user, and I'm just going to leave you alone and not give you the targeted behavior that I'm trying to hide. And this is one of the main ways that these systems prevent partners from finding the bad behavior, because partners are just going to get a sample of the application and they're just going to install it without any kind of like install tracking or referrer ID, and they're just going to see the normal flashlight app without any background clicks or HTTP requests, and without a deep dive static analysis of the code, they may think it's perfectly legit and ship it out pre-installed on their device, and then later on, things change quite a bit once they're out in the hands of real-world users. So, okay, just to kind of reiterate some of the common attributes that we see inside of these campaigns that are giving us fake functionality on one side and different functionality to real-world users. So they need to have some kind of method of determining that a client is a high-risk witness of unwanted or malicious behavior. And I had mentioned previously that one of these heuristics might be that you install too often. This is something that is going to be a key indicator to the bad actors who are managing the campaign, because real users rarely reinstall an app. I mean, even if how often do you get a new phone, right? This might be once a year. Even if you have to reformat or something, you're never going to have more than a few installs in a short period of time. So that's very different than like a sandbox environment, especially run by antivirus vendors. They're generally trying to milk as much information of your app out as they can, so they might be installing dozens of times in a single day. And you can just basically put anyone with a certain number of installs into a bucket that you say, no, you are a high-risk user. You're not going to get the behaviors that I want to give you. And most of these campaigns as well, they create basically a heartbeat that triggers to their API at a regular cadence. And this gives them behavioral information about the user and tells them when you have this information in mass, you can determine who is likely a real person with a real phone and who is a sandbox who kind of like comes on and then kicks off and probably disappears and never shows up again. So you may require a certain number of heartbeats over a specific number of time before we put into a targeted bucket. It's very rare for individual users to be targeted, with the exception of like very sophisticated phishing campaigns. But what you generally get is you put into some kind of bucket based on heuristics that are applied to you, and then that bucket may contain thousands and thousands or millions of installs, and then they target that specific set of installs. So buckets can be based on things like how much I paid for you, what country you're in, how old your installation is. A lot of times with malicious adware, the older users are very likely people who are sticking around because they don't know how to uninstall your app, or they are just like long tail users with like a phone that's just maybe sitting around on a counter checking in with Wi-Fi. These people are the most valuable to fraudsters because they have a reliable connection and they're going to stay alive for quite a long time. They're also very, very unlikely to be an AV vendor. It's very rare and extremely resource intensive to be long tail installing bad apps as an analyst, because I need that phone to keep testing new apps. So that's one of the ways that bad actors are going to like specifically target you. Additionally, the thing that these campaigns they do what I would call meta cloaking. In addition to cloaking on the actual app behaviors itself, the entity itself has many play accounts. They probably have different doing business as registered all over the world, different LLCs that are just basically shell companies, so that they can kind of shift the blame and move their nefarious actions all around, with basically being respawned as a new entity. It's very hard to take these large sprawling shell companies and assign them to a single threat actor. We've done it, and it was mentioned yesterday that we do know of like actual shops that their main business is creating malicious software, but they generally don't present themselves to the public under that brand name. That's like their local brand where they hire employees, and then they go out and enter the various distribution spaces as under different fake names or shell companies. Okay. So let's talk more about Android specifically and the kind of things I would check if I was some malicious software that was trying to hide from analysts. So one of the things I see very frequently is both malware and adware checking your camera. It's very rare for an emulator to have a flash available to the camera info interface. So if I just simply do a check for the camera and say, does it have a flash? Well, you don't have a flash, so you're probably not a real user with a recent phone, so I'm just going to ignore you and not cloak on you anymore. We'll reference a case in a little bit, but it's another very, very common technique is to create a listener for sensors on your phone. These could be light sensors or accelerometers. Those are the most common ones. And what this does is ensures that you're not an emulator. An emulator's accelerometer is not going to have any real data. The phone doesn't actually move and is a virtual device. So if I want to ensure that you're a real phone, I can make sure that your phone actually moves. So I can set up a accelerometer listener, and then track the movements of the accelerometer and set certain thresholds so that I'll only trigger my activity once I've ensured that your phone moves around, that it's actually a phone in a human hand and not some device sitting on a data center shelf or a virtual device that doesn't really exist. Additionally, most antivirus vendors have some kind of custom ROM that they test their malicious software on, and that's because they need to do all types of kernel level hooking to get really low level analysis of what's happening during the dynamic execution of the app. So it's pretty rare for these custom kernels to be named the same as real phones. So I have seen quite often advertising SDKs and truly malicious software phishing apps check your build name of your kernel to see if it matches common build names, or if it has something in it that might be like attributable to an antivirus vendor, or something that they just aren't part of a allow list that they would use to say, well, we're only going to target these kernels that don't contain these names. Another thing that's very, very common is that the CPU x86 to ARM translation checks. Most emulators are run on x86 processors. Most Android ROMs are run on the on ARM processors, so there is a translation that occurs. This is generally done by virtual hypervisor called QEMU. So they will check for this and see if you are translating your processor level instructions to ensure that you're not an emulator. Additionally, the Android emulators will have drivers that have the name Goldfish in them, so they will check the driver files and see if this word Goldfish appears anywhere, and if it does, they'll probably either bail the installation or they're going to bail like their next stage of their bad app. Most bad apps use multi-stage payloads. And there is a risk-reward ratio for this. Every stage that you add to your campaign, you're going to have some failure. Some clients aren't going to be able to connect. They're not going to have enough bandwidth to download the next payload. So there's a trade-off there, and I've seen as many as 4 payloads come down before malicious functionality, with each payload having different levels of checks to ensure that absolutely no possible way am I dealing with a Google employee. Instead, I'm dealing with a real user who has a real phone who's installed me for 14 days. Other things that they may check are just, is rooting available on the device? Almost always an analyst phone is rooted because we want to have super user permissions to get some of the system information. And a lot of time inside of this OS build class, there's, I linked here to the documentation, there's a whole number of parameters that can indicate both a phone that is of certain brands that are rare and maybe something I don't want to target, or CPU information, hardware information, all types of stuff are in the OS build class that can tip me off to emulator. Additionally, there's checks for things like MAC addresses. Virtual MAC addresses common have the same starting hash, so I can blocklist several MAC addresses that I know belong to virtual devices, and then if I check your MAC address and it matches that pattern, I will just simply avoid dropping whatever behavior I'm trying to hide. All right, so let's kind of summarize all of our various techniques of cloaking that we would normally find. So we see that as I just discussed in detail, we have several types of emulator checks or instruction translation checks. Time-based cloaking is extremely effective and almost impossible to circumvent as long as you are not using the system clock on the phone. Some folks make this mistake and then allow us to just push the time forward and get the behavior in just a short time. The effective technique here is to use the server side timestamp rather than the timestamp that can easily be changed on the phone itself. We talked about refer-based cloaking. This is where I'm ensuring that the install source of the person who I'm targeting is a source that I want to be monetizing or be targeting with malicious behavior. And certain system properties that aren't based on hardware, such as branding and names, are very common. Bad actors seem to think that Google only uses Google phones, and they are very often avoiding Google branded phones. Those are phones like Nexus and Pixel brands. I also have seen very, very common technique is app-based cloaking. And this is where I assume that since maybe an app like Instagram or Facebook has over 1 billion installs, and I'm targeting users where this app is popular, I may just assume that only the analysts or testers are going to not have installed these popular apps. So I've seen many times where they check whether the Facebook package or Instagram package or other very popular apps for that geo are installed on the phone. And if they don't find that package name present, they just avoid you. So here's an example. This is a piece of adware that contained a class called AppHideHandler. This is actually not that malicious. They're just trying to avoid some Google policy violations. There's a couple violations here. One is that you're not allowed to hide your icon from the user to prevent uninstall. But that's what this class is successfully does. And so what you can see in this code here is that they check the build manufacturer class. And if that the return value of that string contains Pixel, Nexus, or Google, they will avoid executing the other two functions, which is the invisible app function, which actually hides your app from the launcher, making it harder to uninstall, and the force app open app rating class or method. What that does is that this is another policy violation. You're not supposed to be forcibly trying to get users to review your app. So this open app rating actually calls some functions that would basically set you up to give them a 5-star rating. Pretty simple, straightforward example with very good naming conventions here. It makes it very clear what they're trying to do. So I really appreciated these authors. These are some other cases that I'm not going to go into detail in the interest of time, but I wanted to share with you. And I did include some of the samples that these researchers have gone through great lengths to explain these cloaking techniques in detail. So I'm going to just let you look at this on your own time. But what we find here in this first article is some banking Trojans. Basically, this was a hostile downloader that was downloading a Nubis banking Trojan, and it would look for accelerometer activity and actually record that and determine that your accelerometer activities was active enough that you were a real phone. And then after it had made that determination, it would make a background request to their server and say, yes, I have enough sensor data. Please give me the second stage payload. If you didn't have any accelerometer data, it was actually just the legitimate flashlight or currency converter and didn't do any malicious functionality. The second case here is extremely interesting because I think that this particular adware company, they might have used the most stages of payloads that I've ever seen in a successful campaign. As I mentioned before, the more often you add a second and third and fourth step to your campaign, the more likely you're going to fail. These folks had hundreds and hundreds of millions of users, so they probably just didn't care about the high failure rate. So they would basically start their campaign with a fake icon file, which was actually an encrypted DEX file. They would decrypt this, what looked like inside of the assets folder, a PNG. And they would take this decrypted DEX file and do some profiling of your device, making sure you're not rooted, and that you have a couple other conditions met. I think they were also checking for like Google phones. And that you didn't have developer mode. And if they made sure you didn't have an ADB bridge or developer mode, they would call home, get you a second stage payload, which would do a much more advanced profiling of your device. Then they would give you, they would send that up, and then they would wait, I think about 14 days. I actually talked to this researcher who wrote this article, and they had a very, very hard time. They basically discovered this on accident with an old install and then had a very, very hard time reproducing the behaviors. And that was actually what led to this deep dive investigation, which showed that they were very, very successful in hiding these behaviors from analysts without, you basically had to have a very real phone that had to sit there for at least 2 weeks. This software came pre-installed on a lot of devices, so they didn't have any problem targeting real users, but it was very, very difficult to reproduce as just by downloading the payload from VirusTotal and trying to get the bad ads to show. And these guys weren't actually that malicious. After they went through all of these advanced techniques to get you, they really just opened a DEX file that would just start showing ads at using an alarm manager from the background. It's extremely annoying and disruptive, but they weren't actually doing anything that would really cause you long-term harm or put any of your banking information at risk. So that was my whirlwind tour of cloaking techniques. Hopefully this was informative. I want to spend some time now trying to answer some of your questions and see if I can provide you any other information.
Thanks, Arthur. Very cool. So, folks, questions?
Yeah, Arthur, hi, this is Danek. This was a really great talk. I had one thought during your talk. It seems like a great strategy to avoid this malware, is, root your phone, use developer mode, don't use Facebook, install each app 5 times in the first day you want to use this. And maybe pretend you have a Google Pixel. Is that a viable strategy? Probably not for everyone, right?
Yeah, I mean, The specifics of what they cloak on, I mean, I generalize quite a bit, but they're very specific to the individual campaign. Most threat actors don't want to reuse the same techniques over and over because they can become a fingerprint for them. So yeah, in general, I would say not as, without making an official endorsement, you probably are a little bit safer, at least from annoying advertising, if you use a Google branded phone, only because they really seem paranoid about that. But yeah, I mean, it's kind of silly, but in theory, you really can provide probably not a strong shield, but an additional layer of protection, especially against click fraud and ad fraud techniques by installing an app organically instead of installing it from an ad. By doing a lot of the things that are common, yeah, you probably will defend yourself at least from annoying behaviors. Yeah. So.
Yeah. Thanks for a great talk.
Thank you.
By the way,
hi,
sorry, go ahead.
yeah, sorry. So I had a question regarding detecting emulation by, looking at performance of the, say, the antivirus companies usually use emulated environments on large PCs or PC systems, whereas, a real person's device. So there must be some sort of performance differences between, emulated devices and real devices. So have you seen any of those techniques being used by malware authors?
I haven't actually seen them try to do any kind of benchmarking, although that probably would work. One thing though is that even if you have a very powerful server, like you're running Xeon processors for your emulation, the instruction translation makes things extremely slow. So you may actually meet real world device expectations or actually underperform, even though you're allotted 4 cores of a much more powerful silicon. The instruction translation just makes things really lag. So that might actually even things out. But I wouldn't be surprised if there are some things like that. I have seen actually another interesting one where they did something kind of like that, where they were looking at the install times of your apps and diffing them, because when you boot up an emulator image, you basically create that system image all in one swoop, so that the timestamp for the installs of your apps are usually within a couple seconds of each other, because that image was all built at the same time. So all those apps kind of originated at the device at the same time. So I've seen cases where they were diffing all the install times of certain system apps and determining this phone seems weird. This doesn't look like a natural update, which I thought was I've only seen that one time. That was very rare, but I thought that was interesting.
Thank you.
Thanks, Saksham. More questions?
Hi. I thought it was really interesting, kind of how you're talking about how they looked for some of the differences in the way it's kind of how the emulators work in terms of looking for was it the flashlight or the accelerometers. Are there any kind of is there any kind of progress being made on trying to make the emulators more robust, more accurately model real world devices?
Yeah, definitely. We actually have a senior engineer who dedicates a lot of his time to making sure that our analysis system is as realistic as possible. And it is possible when you're building custom kernels to inject a lot of fake data into the profile so that it looks more like a real device rather than an emulator. So it would be possible to spoof a return value for that, for that flash check, for example, so it looks like a flash is there, as long as you specified it in your build. It's very much a cat and mouse game. So when these kind of changes happen, bad actors, particularly because they're motivated by very high incomes, they will generally monitor our changes and try to adapt to everything. So it very much becomes a cat and mouse thing.
Very cool. More questions, folks?
Hi, Arthur. Thank you for your presentation. I saw, you listed several techniques, the developers may use during the clocking, but I'm wondering, is there any, systematic and efficient, techniques Google use to detect the clocking or to combat this kind of behavior? Is there any?
We do have some heuristics for this. I mean, many of this I don't want to expose publicly because I don't want to give away any secrets. But we do try to mitigate these type of profiling techniques. It becomes very difficult at scale because we receive every single app basically that ever is trying to be published. And as I had mentioned early on in the presentation, some of these techniques are perfectly legitimate, right? So if I set up some type of system to detect when a CPU check or address translation check happens, when I'm focused on malware, it makes a lot of sense. But when I'm looking at millions and millions of apps, I find many hundreds of apps that are big apps that are legitimately doing these type of profilings for compatibility checks or for anti-fraud techniques. So it's the biggest challenge is really sifting out the false positives because it can look very much like you're trying to hide from us when in reality you're trying to reach a different end result.
More questions? So, before we sign off for the session, Arthur, this was great. And even though, security analysts are often using a rooted phone, perhaps, and that's a check that the malware authors develop, I assume you're not recommending that people root their phones.
Absolutely not. No, you want to keep the security environment intact. Don't root your phone unless you really know what you're doing, and use that as a testing phone. Your daily driver should be a healthy stock, fully updated Android phone. That will be much more secure.
I just wanted to make sure that after Zdenek's question, I wanted to just make sure that people heard that. I figured that.
Good. That's a good thing to emphasize. Yeah, definitely.
All right, very cool. So this was really great, and I think it gives me a lot of ideas anyway, which I'll reach back to you guys anyway after this 3 days. But it throws a lot of ideas in my head.
Fantastic. That's actually what I was aiming for.
As we speak.
I'm glad I got the wheels turning on these.
No, the others did too. So, all right, awesome. So thanks so much, Arthur, and. We are, believe it or not, actually ahead of schedule. So, that was fantastic. So, I guess we all deserve a 15-minute break, as Arthur has, gone through this very much on time. So let's take a 15-minute break and sync back up at 2 o'clock Eastern, or just before 2 o'clock Eastern, so we can stay on time. So let's say in about 15 minutes, which to me is 1:57 Eastern. So let's sync back at that time. Thank you again, Arthur. Wonderful talk. And we'll listen to the next speaker in a few minutes. Welcome back, everybody. And it's my pleasure now to introduce Vadim Kotov from Google, who will be speaking about toll fraud for the next hour or so. Over to you, Vadim.
Thank you. Hello, everybody. This session is on toll fraud. It's one of the malware categories. And yeah, let's just get to it. Let's begin with the definition. There are essentially two definitions of toll fraud. One is that apps that trick users to subscribe or purchase content via their mobile phone bill. And another is apps that do the subscribing and purchasing automatically and unbeknownst to the user. And this presentation will focus on the latter because the former is more on the social engineering side of things, about tricking people into, buying stuff. This presentation focuses specifically on the technical aspects and what malware can do to secretly put charges on people's mobile bills. Toll fraud takes advantage of direct carrier billing, more specifically WAP billing. Other types of billing fraud include SMS fraud, which is sending messages to premium numbers. It's, I'd say it's been in decline in the past few years, still around though. And another is call fraud, is making calls to premium numbers. And call fraud apps are fairly rare these days. But the idea is for all the fraud apps of this kind, the idea is the same from a device, and charges are put on the user's phone bill. If you follow the news, you might have read about Joker malware family, which is a very persistent malware family, and it is toll fraud. Every few months, there's an article about it. Okay, so let's talk about WAP billing scenario. As you might remember, WAP, which stands for Wireless Application Protocol, used to be a way to connect to the internet from mobile phones in the pre-smartphone era. Another time, we would go on those websites, they were really minimalistic, and we would go there to purchase I don't know, ringtones, mini games, wallpapers, that kind of stuff. And you would, click on the purchase button, and because the connection goes through the carrier, through the mobile operator, they can authenticate your device and they can just bill you. That's how it used to work. Nowadays, WAP itself is more of a thing of the past, with smartphones gaining massive popularity, and smartphones essentially use the same set of protocols and technologies to connect to the internet as desktops and laptops. But WAP billing, strangely enough, is still around. There are websites with WAP billing enabled that allow you through your phone bill. And this slide shows the diagram of a typical WAP billing scenario. For it to work, the device it must use mobile internet. It must not be connected to Wi-Fi. Because when you use mobile internet, your carrier can authenticate your device, because they provide your internet connection at that moment. So they can authenticate your device, and they can bill your account. A user would visit a WAP billing enabled website. On the website would display something like a purchase or subscribe button. The user clicks on it, thus starting the transaction. Then the billing website would communicate with the carrier and inform it that they want to charge this account for this service or subscription, whatever. And the carrier will send an SMS with the verification code to your phone, and you enter the verification code, the user enters the verification code and clicks the confirm or submit button, and thus completing the transaction. And that's how these charges happen. And then they will be charged on their bill, on their phone bill. This SMS verification bit is not necessary. Sometimes it's just enough to just click on the purchase button. And as you can see here, there's nothing really special going on from the user side. In fact, every single step of this process could be automated using standard Android APIs and done automatically. And in fact, that's exactly what toll fraud malware does. Now, this is the same scenario, is just slightly changed. It depicts how a malicious app would perform a transaction, the first thing a malicious app will do is check SIM operator. They don't necessarily need to do that. They don't have to do that. But in order to stay under the radar longer and avoid launching malicious code on devices that that use different operators than the ones supported by the fraudsters, they would check it just in case, and they would halt the malicious subscription if the operator is not supported. And by SIM operator, I of course mean, by SIM operator I mean two things. One is the country and the other the actual operator, AT&T, Vodafone and whatnot. So the second thing is the malicious app would try to disable Wi-Fi or wait until user disables Wi-Fi, or Wi-Fi disables automatically. Because remember, for it to work, you can't use Wi-Fi, you must have mobile data enabled. And then it's pretty much the same. It opens a website, it can use a WebView to do that. And the website would also be sort of a malicious website in a sense. It would be offering sort of fake digital goods. And it will look like a normal subscription website. It would return some kind of subscription link. Then the malicious app can use JavaScript injection to automatically click on those link or on the button or follow the link. And then the carrier will send the verification code. And in this case, malicious app will intercept the SMS and use the same JavaScript injection method to enter their verification code on the page and click the submit button. And this all can be done essentially, or hopefully from the malware point of view, should be done without user noticing anything. Well, they will notice later when their phone bill is bigger than they expect. Okay, so for the rest of the presentation, we will go over these steps that malicious apps take to do this transaction. And the first thing is identifying SIM operator. Android API provides manage various aspects of the device operation. You instantiate them by calling getSystemService method. And in this case, you can instantiate a telephony manager by passing the telephony service string onto the getSystemService. And the telephony manager has a method getSIMOperator, which returns a string, a numerical string. And this numerical string consists of two parts. One is the mobile country code, and another is mobile network code. And the country code is the actual country. The mobile network is your operator, Vodafone, AT&T, Verizon, what have you. And this is where, and then this numerical code is matched against what a malicious app is interested in. The aforementioned Joker app frequently targets Malaysia and Thailand, and their MCC code, so the first three digits of the operator code would be 502 for Malaysia, 520 for Thailand. And you'd often see these checks device. Sometimes the malicious apps would collect the operator code and send it to the command and control server. And then command and control server will perform the validation and issue the next instruction. It will inform the client on the device what to do next. So next thing is getting on mobile internet. There are two main ways to do that. One is explicit. You instantiate another system service called Wi-Fi service, Wi-Fi manager, and it has a method called set Wi-Fi enabled that takes one argument, a boolean. If you send false, it disables Wi-Fi. If you send true, it enables Wi-Fi. Change Wi-Fi state permission. You might also need access Wi-Fi state permission if you want to do it in a clean way, like shown in this snippet. If you want to first check whether the Wi-Fi is enabled, this requires access Wi-Fi state permission. But then this check is, strictly speaking, not necessary, although desirable. So if you see something like a camera app with changed Wi-Fi state permission, you might get very suspicious, and malware folks understand that. And sometimes they won't use it, which is more innocuous permission, as present in every other app, but allows you to achieve pretty much the same result. To do that, you need to instantiate another system service called Connectivity Manager, and it has a method called get active network info. From that returns an object of network info class, and that object, through that object, you can call a method get type, and then you can and that returns you the type of the connection that the device currently has. For example, you can check if it's not Wi-Fi, then start the subscription. Now, of course, you're going to have to monitor, periodically check this, because if the user is on Wi-Fi, you'd want to wait until they switch to mobile data. And there are many ways to do that on Android. Job scheduler is one way. Alarm manager is another way. So there are multiple ways to perform that polling like this. So between these two methods, it's quite interesting that we are connected to Wi-Fi typically when we're at home, maybe when we're at work or at the university. But during the commute, or when we leave home, go for groceries or whatnot, we typically are on mobile data. That's sort of the lifestyle these days. Well, not these days specifically during the lockdown, but on a normal day. And so if you just sit quietly, if a malicious app sits quietly and just monitors for network changes, it's almost guaranteed that at some point a user would switch onto mobile internet. So they really need to wait. The advantage of the explicit method is of course that you sort of can get on with malicious payload faster. So now let's talk about interacting with the web pages using JavaScript injection. Android API provides a class called the WebView. That's essentially a widget that you can put on your app to display web content. It's very simple. You instantiate it and you load a URL in it. Of course, there are other things. You might set some properties, the size, the location, and whatnot. But at the very basic level, these are two methods that you need to call: a constructor and load URL. And WebView is essentially a miniature web browser. By default, it only just displays HTML, but you can enable JavaScript by accessing the settings of a WebView and calling set JavaScript enabled true. So now the websites that you load, if they have JavaScript, that JavaScript will get executed. Furthermore, the WebView allows you to manipulate web pages using a WebView client. A WebView client is a class with a collection of callbacks. which are invoked at different stages of processing a web page. One such callback is on page finished, which, as the name suggests, is invoked when a web page is loaded and finished rendering. And at that point, you can manipulate the contents of this page, or you can load additional URLs. And if your URL is of this format, JavaScript, and then your JavaScript code, that allows you to execute any JavaScript code, and that JavaScript code will have access to the contents of the page. And this is essentially how JavaScript injection is done on Android using WebView. You might have noticed that at this point there is no explicit way to read. If you want your JavaScript to return something, there is not explicit way to get that information back from the load URL. But luckily, there's another feature, and that feature is a JavaScript interface. You can create a JavaScript interface as just a class. You can create a method in there and preface it with the JavaScript interface decorator. It can take it's just a regular Java method, essentially. But then you instantiate this class and you add it as a JavaScript interface to your WebView. The method add JavaScript interface takes two arguments. One is the instance of the class, and two is the name. That name will be used by the web pages as a handle to your interface. So now, after you've done these two things, a web page loaded in your WebView could call this do something method by doing this. My interface is the name that you given to the JavaScript that we've given to the JavaScript interface. Use as a handle and just access the method through this handle and pass an argument in there. This is a way you can allow JavaScript to execute essentially Java functions. And I think you've covered this type of behavior during the hybrid apps earlier today. There's those frameworks that allow you developing your apps in JavaScript. They use similar idea. And here are some examples of JavaScript from malware. So this one on top, the first one, it accesses an HTML element with the ID pin, and that's the confirmation code field. It accesses the property value, it assigns it a value, and then it searches for another element called submit pin, which is a button, and performs a click, and that's it. It essentially emulates entering a pin and clicking on a button. The second one is a bit more elaborate. It sends MSISDN. You can think of it as just a phone number, MSISDN. And also, as you can see here, checks a checkbox. It looks for a checkbox, checks if it's not checked, it performs a click on it, thus effectively checking the checkbox. And then again performs the submit. Now the third example here is very similar to the first one. The field here is called tag. Tag stands for, I think, tag allocation code, but it's essentially a synonym for the verification code. And but with this addition here, it actually calls a JavaScript interface function method and returns some text back to the app. And essentially they're using here the same idea, except the name is whatever VJS interface. So This is JavaScript injection. Of course, you don't have to use WebView to interact with a web page, but it's easy and it works, and so malware takes advantage of that. Next step in this workflow in the malicious subscripts, and there are 3 common ways to do that. First one is by using a broadcast receiver, which requires SMS receive permissions. The second is using content resolver, which allows you accessing to the SMS inbox, and that requires SMS read permission. And finally, using status bar notifications, and that requires byte notification listener service permission. The difference between SMS receive and SMS read is that receiving SMS means that your app can process an SMS at the moment it is received. SMS read, though, simply allows you to read the. Let's go over all 3 of those methods. So first one is reading SMS using broadcast receiver. A broadcast receiver is a class that essentially provides callbacks and responds to various events that happen on the device. The main method here is onReceive, and it is invoked whenever a broadcast is being sent out. It takes 2 arguments, contents and intent. Intent contains information about the event that took place. You can access the action property by calling getAction method. And typically in SMS, in broadcast receivers, reading SMS, you'd want to verify that SMS received action is the action that's been broadcast. Once you've verified that, you can access extra information in the intent. To do that, you call getExtras on intent, which returns an object of class bundle. And this is, think of it as a hash map, essentially. You can access its elements by keys. And the next thing that SMS receiver would do is access the so-called PDUs. A PDU stands for Protocol Data Unit. And these are essentially, it's an array, first of all, and these are essentially chunks of text from which a full SMS message is made of. What you can do is iterate over the PDUs. You can then call create from PDU method of SMS message class to get the actual SMS message object from a PDU. And then you can call get message body to get the actual text of the SMS. All you need to do is to sort of iterate over the PDUs and append the pieces of the SMS body to your SMS text. And that's it. One thing you might notice sometimes the toll fraud malware does is call abort broadcast. This method will actually stop the broadcast from spreading further in the app. You see, when the broadcast is sent, there are many apps and there are many classes within an app that might be interested in various events. So a broadcast simply goes through however many apps, however many broadcast receivers you have on your device. And a bot broadcast simply stops it from going any further. Why do they do that? Well, they do that to stop the broadcast from getting picked up by the, for example, notification service, so that this notification on top of the phone doesn't pop and the user doesn't get suspicious. How do you know that your broadcast receiver will be the first in the stack to process a broadcast? To answer this question, we need to look at how the broadcast receivers are set up. So we instantiate our SMS receiver. This was our SMS receiver. So we instantiate it, and then we create an intent filter. Intent filter simply tells, it specifies which actions a receiver is interested in. In this case, we say we're interested in an SMS receive action. And also some additional properties. One of them is priority. And in toll fraud apps, you'll often see a priority set to the maximum integer, the biggest integer supported by the platform. And that means that it will be the first to process the broadcast. And then you call register receiver to make your app aware that this receiver is watching out for SMS received events. It should be noted that this does not work on Android since KitKat. You can't just abort a broadcast. You need to be a default SMS app. And malware folks know that. And what they do is they try to impersonate messenger apps. They would take an open source messenger. One of the popular ones is Quick SMS, abbreviated as QKSMS. It's an open source project. It's available on GitHub. Many legitimate messengers are built based on it. Apologies. Many legitimate messengers are built upon it, and they add malicious code, and then they change the name and the logo. These are some examples, and then they use spam, use malicious advertising, and trying to trick users to, hey, try a new fancy messenger app. And these are some of the pop-ups you'd see on the phone if you were to install one of those apps. One is it will ask you whether you want to allow them to view SMS messages. That means that you are granting them SMS read and receive permissions. And another one is that they change the default SMS app. And once you do that, you give them essentially full control over the receiving and sending SMS and processing incoming SMS messages. So that was the explicit way, the most common way of receiving SMS. Another way is using Content Resolver, or rather a combination of Content Observer and Content Resolver. Now, Content Observer is a class that, as the name suggests, allows you to monitor changes in a specific type of content. It has a method called onChange, which is invoked whenever a change happens in a particular type of content you're interested in. In this case, we're interested in the contents of your SMS inbox. Let's look at the onChange, the body of the onChange method here. We instantiate Content Resolver simply by calling it Content Resolver method. Now, Content Resolver allows you to query it. It's essentially, it's very similar to querying a relational database, like something like SQLite and whatnot. You first specify what kind of content you're interested in. In this case, we're interested in SMS inbox. Then you specify which columns of the table you're interested in. In this case, we're interested in body, message body, and date, the date the message was received. Then that read column is 0. I'm sorry, read. It means that if read is 0, it means that the SMS hasn't been read yet. It's a new SMS. And this sort of additional parameters, this one sorts the results by date in descending order, so that the most recent one would be on top. And that returns a cursor, and you call move to first to get access to the very first row returned by that query, and you just get the column, the contents of the column body. To do that, you first get the column index, and then you just get the string from that column index, and that's the SMS contents. And you can just pass it on further into the extract function that extracts the confirmation code away about the connection to the content resolver. And effectively, you've read an incoming SMS. This snippet here shows how to set up your observer. So we instantiate our observer. It takes 2 arguments, a handler and a context. It's just you can just create a new handler and pass whatever context you have handy at the moment. And then you call a method of get content of content resolver class called register content observer. And you tell it that you would like to monitor for changes in this type of content. So, and you pass the SMS observer as the observer class, or rather, which class to be called when a change happens. And whenever a new SMS arrives, a change will be detected, and the SMS observer will be called, the onChange method will be called, and you get access to the contents of the SMS. Effectively, it does the same thing as the previous method. There's maybe some milliseconds of delay between the SMS arrival and you're accessing it through this method. But overall, it's not, the difference are negligible. And the only difference from the malware perspective is that there's no way to abort the broadcast. But again, aborting broadcast is more of a static touch, right? It's desirable. It allows you to stay under the radar to be as stealthy as you possibly can, but it's not necessary. And I don't know, it's given how many random pop-ups we get these days, it's really easy to miss some, okay, some message came along, so what? Really not that big a deal. Finally, the third way to get SMS, this method is particularly trendy in the past, has been particularly trendy in the past year or two, is by accessing the notification, status bar notifications. Let's get back here real quick. This thing right here, by default, the contents of an SMS message will be displayed in the status bar notification. And if they're displayed there, that means they can do read. How to do it? Very easy. You need a notification listener service, an SMS notification listener. And there is a method called onNotificationPosted, which is called whenever a new notification is issued. It takes one argument, that is status bar notification. And here what malware usually does when that happens. Status bar notification has a method called getPackageName, which allows you to find out which app is responsible for this notification. Meanwhile, there's a method called getDefaultSMSPackage that you can access through telephony and through its SMS field, which returns a string containing the package name of your default SMS app. So you compare the two, and if they're equal, then you know that the notification came from the default SMS package, but that is an SMS notification, which means that you should read it. To do that, you call getNotification method of the status bar notification class of your status bar notification argument. That gives you the actual notification. And then the notification has a field called extras, which is also kind of a hash map. You can get char sequences from it by accessing the string key of type string, in this case android.text, and this is how you get the contents of the notification. And if it is an SMS notification, the contents of the notification is the SMS text. And another thing and then a malware would pass it to whatever code further to further process the SMS text, and then it might call cancel all notifications, so that same idea as aborting broadcast, essentially. Just don't allow this notification to proliferate any further. And so this, I think, yes, this concludes the theoretical part of the session. In conclusion, a final remark is that what we've looked at so far, these are fairly clean. This is fairly clean Java code, just to demonstrate to you what are these API methods and how, in what context are they used. But in real world malware, most of the time, it will be obfuscated. And we'll talk about obfuscation at great detail tomorrow. We'll cover common obfuscation techniques on Android. And so we prepared a sample for you to work on. Now, this sample is a fake SMS app, which is really a toll fraud backdoor. It is a toll fraud app, and it has additional other types of billing fraud, SMS fraud, namely. And the challenge in these kinds of apps is that, of course, they're based on an some open source messenger, and the malicious code is really only small. The trick is to find the malicious code in there and understand what it does. Now, so this sample that I mentioned, it is also obfuscated, but for this session, we actually de-obfuscated it, and we recompiled a clean version. So you'll get to analyze a clean version today, so that you're not preoccupied with de-obfuscating it, because it's not the point of this particular topic. Tomorrow we will see how to actually de-obfuscate. We will see the original sample, take a look at the original sample, and we'll see how to defeat the obfuscation and how to get this. But for now, I'm not. Let me see if the sample is in the chat. Yes, the sample has been shared on the chat. You can download it. The password is Dartmouth, and you can open it, and we can get to analyzing it. I will show you a couple of tricks that might be of use when analyzing these kinds of apps. And please let me know if you have questions or troubles with opening the sample or accessing the sample or decompressing it. So I doubt that we will be able to cover all of it during the remaining time, but I think we can continue during the lab session. I'll stick around for I'll stick around for the whole duration of the lab slot. But for now, I will try to give you a few hints and sort of set you on track to reverse engineering this app. But before we get to that, perhaps I should answer, maybe you folks have questions about the theoretical part of the presentation.
Thank you, Vadim. Again, great session. So I'll open up the floor to questions from students and postdocs who are attending. Guys, go for it.
Vadim, maybe just a quick question. This is kind of, my question maybe it's not that technical, but just, like a common question. So to me, we have the malware like the SMS fraud, right? And they're trying to get the victim to subscribe their service and to get the money. But that, just specifically in the US, the users always subscribe the plan like ATT or Verizon, like the monthly subscription, right? So maybe those kind of malware cannot get money. I just mean money from this kind of victim. But maybe I know that they try to try to behave like try to be the default SMS messaging app to control the service or to get their credential information, something like that. But just to this content, so do you think that maybe the SMS fraud just to get the money maybe not that popular in the US or some countries like this?
That's a very good question. Indeed, toll fraud, SMS fraud, the sort of billing fraud apps are not that widespread in the US, although it does happen. I would say the majority of attacks of this kind happen in the Southeast Asia, but we saw examples in Europe, for example, and in other places. It doesn't really matter what kind of the precise financial relationship you have with the carrier, how exactly are you getting billed. For example, there are plenty of paid SMS services, right? You send an SMS to a premium number, your phone bill is charged. In the billing fraud scenario, there are two instances of the attacker. One is the malicious app that sits on your phone, and another is this the premium service or this premium subscription or this WAP billing website. But these are also controlled by the same attacker. They sort of provide you this fake service, then they themselves subscribe to the same service, and then you essentially pay to them for their fake goods. So that's how they make money. And I don't know how that changes from carrier to carrier. But if a carrier has good protections in place, for example, against that, then attackers will probably not support that carrier. They specifically aim those carriers which allow this kind of transactions, and there's no shortage of those.
Thank you. That's very interesting. Thank you.
More questions?
Yeah, I have another question. Thank you for your presentation. It was very nice. And I want to know that what does Android do now to prevent these kind of attacks from happening? So what are the approaches to detect this kind of, for example, you were talking that there is a callback function for the web view for the on page finished, and then in that function you can load a URL that you can load your JavaScript code. So how does Android can detect these kind of misbehaviors now?
The main problem with malware like this is they really don't do anything sort of extraordinary. They using the same things that any legitimate app, same functionality that any legitimate app would use. All those billing scenarios, they exist in legitimate apps, and the problem is not so much on the technical side of what can you do on the device, but rather how can you prevent fraudsters from putting up their malicious content. So the embedded protections are, for example, now if you would try to send an SMS to a premium number, you'd get a pop-up that would warn you that, hey, are you aware that you're sending, that you might be charged for that SMS? Or, for example, the policy on Google Play forbids most apps from having SMS permissions unless it's a SMS messenger. And so that is a great challenge, and I don't think it's a technical issue. It's a complex issue that can't only be tackled on the device itself.
Thank you, Vadim. And I should also mention to Shayan and others on the call that, Google obviously cannot share everything they're doing. So let me also,
Oh, you're right. Yeah.
So, but I'm sure that there's a lot going on. Otherwise, this team would not be there. So more questions. All right, great. So if there aren't more questions, we will thank Vadim for an excellent and very insightful presentation. And I think yesterday, so we're now approaching the lunch break time, lunch in California, go get a coffee or cookie or something over on the West Coast, on the East Coast. And so what I'm going to suggest, if it's okay with everybody, is that one of the things we discussed yesterday was that some of the students on the call might download Android Studio, JADX, etc., and start playing around with some of the samples that were provided yesterday. So what I would suggest is we leave the call open, but without recording, and so that students can interact with any of the Google folks who are here, and share their screens with them and get some ideas on what they're doing right, what they're doing wrong. I'm hoping the students have done this because I haven't checked anybody's homework on this, but hopefully you'll get some questions. But also, I think people should feel free to move in and out, both on the Dartmouth side and the Google side, because sitting for 3 hours now at a stretch is, starts feeling a little bit like being in an airplane, even though we're getting very high quality information and learning experience. But I think, I at least am going to get up and take a stroll for a few minutes and come back in 30 minutes or so. But people should, use their own judgment on how what they want to do over this lunch period. Okay. So we're going to leave the call on. I'm going to turn my video and camera off, but everybody, go for it. Okay. Welcome back, everyone. My clock shows 4 o'clock. So it's time to start again. I hope everybody had a good lunch or a good snack, depending on your time zone. So our next session, we are happy to welcome Arthur back to speak to us about ad fraud. So Arthur, over to you.
Thank you. Glad to be back again. Very interesting topic this time about advertising fraud. Very wide-ranging and complex subject that probably we could spend the whole 3-day course finding various aspects of this to talk about. So I've been trying to distill this down to what I think will be most interesting and or essential for us to learn. So what I'm going to first do is kind of try to give you a context of how modern digital advertising is working right now, so that you can really understand what's going on when you hear about fake clicks or fake install information. So first we're going to talk about just the general operations of real-time programmatic ads, and then we'll talk about fake clicks, and then we will talk about another fairly niche topic, install attribution fraud, which is actually quite common, where various publishers are stealing quite a bit of money based on your install activity from various ad exchanges. So first thing we're going to do is just give you a whirlwind tour so you can all be at least familiar with the modern digital advertising space. Some terms I want us to ensure we all kind of have a common definition for. SDK providers are primarily the people on Android doing most of the advertising. These are plug and play software kits that you install into your app and provide you with advertising with very minimal configuration from your side as the app developer. You generally provide a partner ID, a couple other parameters that you'd want, the type of inventory, and some frequency parameters, and you're basically plug and play ready to go. For our discussion here, publishers are going to be basically an interchangeable term with app creators. This term becomes very sticky in terms of advertising. The publisher can be defined a number of ways, but for us, it's the apps. The advertiser is, of course, the brand who's filling the advertising slots, and these are also in some documentations going to be referred to as a brand or as a marketer. And you know, they're either promoting themselves as a brand or one of their specific products. An agency is basically an organization that helps the advertiser get themselves out into the ad space. As you will find out, bidding on ads and placing ads is an extremely complex measure, so you generally outsource all of this work to a marketing agency who then develops your campaign for you, creates what are called creatives, which is actually like the images and text inside of the ad. And these agencies are famous across all platforms, even legacy advertising like television, right? That's where the show Mad Men came from, was they were an advertising agency. So that term basically tracks still to the modern era. DSP, a little bit more of an esoteric term. This is a demand side platform, and this is an aggregated platform that helps advertisers and or advertising agencies to get their campaign in places that they want it. So a DSP will provide an advertiser, you can give the DSP like, I want to target, say, homeowners in this zip code with this estimated income, and the DSP will try to get those ads in the places where they think that those individuals meet that criteria. The sell side platform is basically the exact inverse of that. That is for app publishers and SDK providers to be able to tell the exchanges, hey, we have an ad of a certain size or of a certain type available. Give us your bid, and we will try to fill you at that price in our platform. And that platform will tell the exchange also like what app it's going to be displayed in, the type of app, what countries, that kind of thing as well. The exchange is where these two platforms meet. Think of it as any other commodity market. The modern real-time bidding market of ad exchanges is almost identical to, say, orange juice futures, pork bellies, equity markets, options exchanges. They're not much different. You have these two platforms doing bids and offers together, and then they come to a common price, and the exchange is made in nearly real time, very, very, very quickly. Attribution providers and verification services, these are third-party services that both the supply side and demand side use to try to get a source of truth that's independent of their platform, right? There's a lot of opportunity to want to lie to each other to make more money. So these services try to provide an independent accounting of what's actually happening inside of the ad exchanges. And generally these travel along with you inside of your app, tracking what's going on, or inside of your SDK if you're on the demand side. So here's a fairly simplified version of what modern ad exchanges look like. I pulled this down from Wikipedia article on it. It is, in fact, a little bit oversimplified, but for our cases, it works actually quite well. So over here on the left side where we see this individual user with his tablet, this is a person who's loading an app or a website. And inside of that app, there's generally an SDK. They would be, the SDK for our purposes is most of the publishing content. All of these aqua colored bubbles are generally going to be provided by an SDK and their partners. They talk then to the commodity market. Think of it like the New York Stock Exchange for ads. And they are going to present their offers for what spaces are available to brands and agencies who want to provide ads. And then those folks are basically, there's a whole bunch of demand side platforms all talking to each other, and they're probably all reselling various things to each other. And then they bring those items to the exchange and say, hey, we want to fill our, say, ads for housing mortgages at this particular prices, and we're willing to pay this price for these type of users. And then this, I've added in here these verification attribution providers. These are companies like AppsFlyer, WhiteOps, Coachava. Basically, they are there as third-party arbitrators of what they think is the actual clicks being made, and they provide basically a service to try to provide an independent accounting of what's happening. And then basically the publishers and the agencies both sign up with these services from each side to try to ensure that they can get a source of truth that they can actually trust. Again, this is a very simplified version. I'll leave this here. I'll place this in the chat later, but this was a good infographic I actually came across very recently where this blogger who specializes in marketing, I haven't really read much of their content, but they did a very good job of mapping out the relationships of the ad tech industry, which is incredibly complex and has grown exponentially over the last 6 years. And now they have mapped out the relationships between 8,000 different advertising entities, somewhere around there. And this massively high-res image kind of gives you a real perspective on what's actually going on in these exchanges and how complex these relationships are. And of course, the more complex the system, the more likelihood there's going to be problems with it and areas for fraudsters to exploit. And that's what's going on for us. If you want to kind of get yourself more familiar, because I'm just really giving you a whirlwind tour of what digital advertising is like, these are some links which you can peruse on your own time that should help you understand quite a bit more about real-time bidding systems. Real-time bidding systems, programmatic advertising isn't the only way to do digital ads, but it's definitely the area of digital advertising that's most ripe for fraud and where most of the fraud is happening in today's world. So feel free to look at these links if you would like to learn more about these very complex topics. So getting to our specific interest, Android advertising. We have basically 5 ways in which we are tracking and trying to defeat annoying and fraudulent advertising on Android. The one major area is disruptive advertising. You're probably all familiar with this on many verticals, not just on Android, but this is like pop-up ads that seem to come out of nowhere, or they pop up outside of the context of your app. Maybe you unlock your phone and all of a sudden you see an ad, or you see browsers opening up from the background showing you many strange ads. This is a very common occurrence, something we've focused on a lot recently, and I think we've done quite a good job of stopping this, but it continues to persist. Attribution fraud is very specialized case of fraud where apps are paying for distribution and they pay a marketing agency for each install, and the fraudsters are tricking that agency into saying that they were the ones who provided the installation, when in reality the installation came from either a different place or was organic from the user, and they've mocked it up to look like it was their install. We're going to go into that in a little bit more detail. Programmatic clicking is probably what you're most familiar with, the cases that other folks on my team have talked about. This is what they're usually referring to when they talk about ad fraud, and this is generating artificial clicks using either JavaScript or Android API to trick the ad networks into thinking that a real human was interested in the ad and clicked on it and went to your site or landing page. This really only works against payout models that are pay-per-click or what's called CPM, which is the cost per 1,000 impressions. There's another model which is pay-per-conversion. Programmatic clicking doesn't necessarily work as well there. There are some campaigns that are that advanced, but that a pay-per-conversion would be where you would actually fill out a contact form or actually purchase the product, and that's when you're getting paid. So these campaigns don't focus on that as much as they do on generating as many impressions and clicks as they can, because a lot of the payouts are based on that. Hidden ads is a similar thing. They're trying to increase the impression frequency. And so while you're using an app or using a background service, they will launch very small or hidden web views and basically just keep showing ads to try to inflate that those 1,000 impression marks, because you're probably getting a few cents to a few dollars for every 1,000 impressions you show. Spoofing is another thing that is very specific to the real-time bidding exchanges we talked about previously. This is where you're providing false information to the exchanges and telling them that you're going to show ads, say on an iPhone when you're really an Android device, or you're going to display them in an app that's not really an app that belongs to you. There are some industry remediations for this. They're not widely adopted yet, but one is called app-ads.txt and ads.txt. These are basically attribution files that are publicly available to say, this is how I'm advertising within my app, so that the exchanges can know that someone's bid for your app is fake. The people who are adopting that technology are doing a very good job of remediating this spoofing, but it's not yet widely adopted enough to make a huge difference. These two areas are what we're really going to be talking about today, mainly in the interest of time, but also because I think these are probably some of the most interesting abuse vectors from a technical perspective. All right, so let's get into programmatic clicking. When you do fake clicks on Android on ads, you do actually set many of the similar techniques that Vadim had talked about in the toll fraud discussion. You basically have to find a way to either get a JavaScript interface to load, to evaluate JavaScript that's going to perform a click event, or you can use a view, an Android view, to perform a click directly, or you can use one of our motion event API calls, which allow you to dispatch events. All of these methodologies have very legitimate reasons that you would want to deploy them in an app, but they're also all abused for programmatic clicking. So here's a sample that I like very much. I think the programmers did a very good job of labeling their fraud, so it makes it a very good example for us. This is a fake class here, com.google ring services ADK, ad SDK. The only thing that's true about this is that it's an ad SDK. Even that is actually a lie. It's first-party code, not an SDK that was provided by anyone. And what they're doing here is they are defrauding, well, in this case, they're actually defrauding Google's AdMob network. And you can see here up on line 317 that they are initiating a call to our AdMob class to show an interstitial ad. An interstitial ad is an ad that pops up in between activities, like if you're playing a game and you win a level, between the closing screen of that level and the next level, you might see an interstitial ad in between there. So what they do is they make a call to show this ad, and they've set up this ad listener. And when they've determined with their listener that the ad is opened, they actually parse some server-side JSON that they send down to the app. And one of those values is a bool that tells it, is this an automatic bot click? And should I be clicking on this ad here? So if that value is set to true, which they do based on certain conditions, as we talked about in one of the prior sessions with cloaking, right? They don't do bot clicks on emulators, but they may do it on a real phone. So if they return this bot click is true, then they're going to say, okay, well then I'm going to run my click methodology. And you can see here that they, on 343, that they use the send pointer sig API call to set up a motion event that basically is the equivalent of a user's touch onto the screen. And once this is run, the Google interstitial ad will receive a click. Its on-click listener will be received, and it will act as if it was clicked on by a real human. AdMob has done some amazing work in mitigating this type of fraud. It's far less effective than it used to be, but for all intents and purposes, this does create clicks on AdMob ads. Here I've linked some research, very in-depth research on many of these programmatic clicking techniques. I would like to expound on all this and tell you all about it, but this would take many, many hours. So I'm just going to link this here. And if you're interested in advertising fraud, and it's a very broad area of study, I'd recommend checking out some of these articles from some of the third-party antivirus vendors. This Primo campaign was a multi-$100 million campaign that was across many, many networks. The samples that they highlight here go against Twitter's MoPub SDK. They have a demand-side platform of their own, and basically this software was making calls to that network saying, give me an ad, fulfill it under these conditions, and then using dispatch touch event to click on those ads and generate quite a bit of revenue for these fraudsters. This other campaign that's highlighted here by Sophos is very interesting because they, in addition to doing fraudulent clicks, they were also impersonating iOS devices, sending up to the exchanges that they were an iOS device when, in fact, all of the apps were Android apps that were published on the Play Store, so they were not iOS users. iOS in many countries gets a higher price because it's assumed that iPhone users are buying more expensive phones than Android users, so many advertising networks will pay a premium for Apple devices, which is why they were doing it there. And they were also lying about the app itself that they were. So this was a very, very sophisticated spoofing technique that also involved programmatic clicking. The Techia campaign was very interesting because it actually popped up in response to some improvements that we made almost immediately. We made quite a bit of improvements to our detection of automated clicks, and we found that some of those improvements were mitigated by some of the strategies deployed by these fraudsters, which seemed to be directly in response to our changes. And they started hiding a lot of this click fraud inside of JNI calls. So they would hide the click APIs inside of native files, and then use the Java native interface to interface with these very heavily obfuscated native binaries. Again, these would also only trigger under very specific conditions and would not be easy to find in like dynamic analysis. All right, so that was my whirlwind tour of programmatic clicking. Now I'm going to get into a little bit more of a sophisticated topic of attribution fraud. This is where the refer of an installation is changed artificially to an attribution network. So this doesn't involve really any Google properties. What's happening in most of these cases is that the fraudster is lying to a third-party attribution network. The biggest of these are like AppsFlyer and Coachava, and another one called Adjust. Those are probably the biggest Android providers of attribution information. So these fraudsters lie to those companies and try to trick those companies into giving them credit for the install, and then those companies provide that information to either exchanges or to other networks who then pay out for this fraudulent information. So a referrer, generally speaking, I think many of you are most familiar with it inside of your browser. And I think it's good to step back and talk about referrers so that we kind of have an idea of what's actually changing. So when you're browsing like a social media site like Twitter and you click on any link, you're probably going to see appended to that destination URL, UTM source that says twitter.com, right? That's basically how referrers work on Android as well. We have both an HTTP API, which is fairly secure, and then a system of broadcast intents and receivers that is fairly insecure and has been deprecated, but is still used by these Attribution works for reasons I'm not going to speculate on. And because they continue to use this legacy system, it is highly abused by fraudsters, and we'll get into how that works. Also, if you are to take a look at the HTTP specification, they give you quite a good definition of referrers and can teach you quite a bit about it if you're willing to dive deeper into this topic. So here's how this generally works, right? Let's say that I'm a user and I really want to play Angry Birds. Angry Birds is a heavily promoted app and very, very popular, especially many years ago. So I go to the Play Store, I search Angry Birds, I click on the install button, I install it. That would be referred to as an organic install, and the referrer would either be organic or it would be null, right? We would have no referrer because no one referred me there. I'd searched for it and I installed on my own. And so here, during that process, we have this bad guy who's probably sitting as a different package on the phone inside of an SDK. That's probably his location. So he's sitting inside of an SDK and he set up a broadcast receiver to say, tell me about install events that happen on the phone. So there's an intent filter called package added. So anytime a package is added, I can listen to this. I can listen to this event, and my app can be aware that this Rovio Angry Birds package was added to my phone. And when I get that event, I say, oh, okay, well, do I have any relationships with anyone who's promoting Angry Birds? Oh, turns out my partner over here, they are paying me $6 for every Angry Birds install in the United States. So I will say, okay, let me get the time from my intent receiver that this package was installed. I'm going to set up a fake request to our attribution company and try to tell them that I was the one that installed that. And the way I'm going to do that is I'm going to send this referrer broadcast, which is not validated by any party. You can basically, as any entity, send a referrer broadcast as if you were the Play Store referring. This is why this has been deprecated. My window's a little obscured here, but I linked I have a link here that talks about this. We strongly recommend that everyone move away from this install referrer broadcast API. We are not seeing wide adoption moving away from it yet. I'm not going to say why they're not moving away, but it's very strange. And this continues to be abused even today. Our detections on Play are quite good for this type of fraud, and we've removed many apps for trying to pull this off, and we are seeing quite a bit of decline in it, but it does continue to happen. So let's recap how this fraud happens step by step, right? So the first thing is, if I'm a fraudster that's doing this, I need to establish some type of relationship with a network that does pay per install ads, because otherwise no one's going to pay me for it. So I mean, if I could send out fake broadcasts all day, but if no one's going to pay me, it's not worth my time. So once I have that relationship, then I set up my package added listener, and that intent filter is running, and it's going to listen to the newly added package event. I check to my own server, is this a package that I would want to promote because someone's going to pay me for it? If that value returns back true, then I set up another fake request and send that out to the attribution provider. What I don't actually do is send that usually to the provider directly. What I do is set up a broadcast that makes it look as if my actual legitimate ad campaign was executed. So if we go back to the last slide, right, my partner ID is going to be, on this case, source U. So when I make my broadcast, I say, hey, that Angry Birds installation, it had a referrer value of source U. And an attribution company records that because they're listening. They have their own broadcast. They have their own intent filter that listens to this specific install referrer broadcast. And when they hear about it, they say, source U gave us an install of Angry Birds. And in many cases, they don't do much to verify this information, and they just end up paying, or they do some kind of accounting at the end of the month and decide not to pay. It's very dependent on the network. So let's look at some code that would be, this is like some very similar to real code, but it's just like some mock code that I made on how this would work. So assuming that you have a package added receiver and this code is reachable to that package added receiver. So once my method A is aware that this new package is added, and that this package added is promoted on my network, so I've met all my preconditions for getting paid, then I'm going to set up a new intent that says, hey, I am going to broadcast some refer info from this package, which is the Play Store, Android vending, and it's install refer info. And then the attribution network listens for this broadcast, but they have no way of determining that this broadcast came actually from Android vending. They only just receive the broadcast blindly. This is why we recommend for them to use an HTTP request instead of listening to the broadcast, because the HTTP request is, it's transmitted over a secure socket connection, and it's you're communicating with what you believe, assuming like no DNS poisoning or ARP cache poisoning, that you're talking to the right entity, which is the Google Play Store API, and not just some random third-party package. With these, the way that broadcasts are kind of made for Android, they're not really made to be secure. They're inter-process requests. They're not made to be secure attribution requests. And so the use of them as secure attribution requests is very problematic and something we strongly recommend against. One thing to point out here as well is that the key here is that their intent includes this Android vending package. And what we'll find from most fraudsters, they do a very good job of obfuscating this portion of the broadcast so that we don't easily pick up that they're doing fake broadcasts for this, because you could do a broadcast intent for all kinds of different reasons. I mean, literally thousands of different reasons to do a broadcast. So the key that this is fraud is that they're broadcasting as the Play Store. So we most often see that this value here is obfuscated. So here we see an app that has an SDK that was doing this type of fraud. And this is the manifest of the app, which I pulled off the JDEX decompiler. And the app has an intent receiver that we talked about before that is tells the app when packages were added and when packages were removed from the phone. So they use this package added listener here to do the very process we just described. And if someone was asking me to investigate this SDK, and I was looking at them specifically for this type of fraud, this type of filter somewhere in the app, either dynamically declared or statically declared in the manifest as it is here, is one of the key factors that I'm looking for, right, to determine that they're doing this type of fraud. So since the receiver is registered in this namespace of the Archie native SDK, this is where I would start investigating the app for potential fake broadcasts. So generally, I just pop open this this part of the app, right, this package inside the APK, and I'll just search, did they have a plain text reference to install refer from Android vending? Yeah, turns out it's right there. So it's a very straightforward case why I'm using it for illustration. This doesn't always work out this great, but you can see here that they have some dynamic strings that they set for the values that are specific to the campaign. And so they make, once all that receiver logic that we had previously discussed has been established, then they say, okay, all the conditions are right. I'm going to make my broadcast as if I'm the Play Store, and I'm going to do that with these flags that say that I'm the referrer and that my referrer are these constants that are related to the campaign specific to that app. And that's why they first need to check with their own network, like, hey, what's our partner ID for, say, Amazon.com installs, and how much can we get paid for it? And one of the ways that people got caught for this is that there was a huge story about this a couple of years ago, and the way that those folks really got caught was they were doing this for a very long time in a very controlled manner, and something must have broken on their system, or they decided to just go hog wild with their fraud, and they were targeting users specifically and using quite a bit of advanced cloaking, and somehow that got turned off, and all of their apps were just making these requests in a flood nonstop. Well, they had many hundreds of millions of active users. So all of a sudden, these attribution networks started receiving like billions of installs of Amazon.com. They couldn't understand where this was coming from. And so operational failures like that can get you heavily exposed. So this is another article from another third-party company that explains the details of this in some greater detail. Fairly interesting article. And then here's a BuzzFeed reporter who reported on this and blew up this story from many SDKs that were in many popular apps that were doing this exact type of fraud. And this is a very interesting story, and I encourage you to read it if this type of fraud is something that interests you. Quick tip of time here. Okay, so that's pretty much the whole story here. I've included many samples from each of the areas I talked about. This app is the app that we first looked at that does the programmatic clicking using the send pointer SIG API. Here's a pre-mo sample. This you will find fraudulent clicks inside of the MoPub SDK. If you search for the dispatch touch event API, you will find some correlated code that looks very similar to this first sample here. What's very interesting about both these samples, it can probably be a research topic on its own, is that you will find that these programmatic clickers, they have to set XY coordinates for the clicks. So they often use math random to set these so that it doesn't look like the click is always happening from this very static location, which would look very weird. The ad exchanges generally record the XY location of a click to prevent fraud, right? Because the user is just randomly going to click inside the box, and that is going to develop a very random and organic looking pattern. And what we found at scale across millions and millions and millions of instances of this is that math random does not look random at all. In fact, it looks very much like as if they set hard-coded coordinates on the screen. And we're able to see this by analyzing millions and millions of samples, that math random is not in fact random and uses definitely some kind of deterministic algorithm at scale across billions and billions of instances. So I found that very interesting. This third example is the example from the campaign that was spoofing as an iOS device. And then this is the Techia sample. I do not have a decoded sample, but this is the example where you will find a very, very obfuscated ELF file, which once you de-obfuscate the strings inside that ELF file, you will find that they are also dispatching touch events using the Java native interface. And then this app here is the same app we looked at in our attribution fraud section. And there you can see the same receivers that I highlighted in that same request to broadcast as a fake referrer. So yeah, I think we got running a little bit ahead of schedule, but I think that it is now time for your questions.
No, that's great. Thank you, Arthur. And let me open the floor for questions from people in the audience. You know, I'll start with one. It's, you know, when you talked about the pre-ammo campaign, you'd mentioned that this was really something that was generating millions and millions of dollars. I forgot the exact amount, but it seemed quite substantial. So in cases like this, there are basically, you know, one is to, of course, stop the fraud, but another is to actually take appropriate legal action. Of course, based on the jurisdiction where the criminals are involved. I mean, do you guys do anything, you know, on the latter front? I mean, the technical front is one thing, but the latter front would potentially, you know, serve as a strong deterrent.
So it is very, very, very difficult because mainly of the location of these publishers. They also have generally set up many, many shell companies, as I had talked about in there. So a lot of times it will be very hard to prove in a court of law that this particular software publisher was the one benefiting. It could probably be done, but we haven't seen much interest from law enforcement due to these complications in this area. There is a very famous advertising bot called MethBot. And I believe that those folks did end up getting prosecuted. They were somewhere in Europe, I think Sweden, I don't remember exactly, maybe Denmark. I don't remember exactly where they were, but I believe that the folks behind that particular botnet that was doing click fraud, they did get prosecuted, and I think they did end up with a couple years in prison for significant fraud. Again, they were only able to pin on them a fraction of what the estimated value of the botnet was. And they had made some very serious operational mistakes, and then of course operated in a country where the authorities wanted to cooperate with the researchers, right? In many of these jurisdictions, the authorities do not want to cooperate with you or help you, or there'll be no jurisdiction locations. And we actually see a lot of these shells are set up away from where the company even is on purpose, right? They may open up a shell company that's paying out to the Isle of Man or to Seychelles or Turkey or Venezuela or something in order to prevent extradition or having like the legal issues fall back on them in their homeland.
Got it. Okay, well, yeah, not a technical question, but I figured you might know the answer.
Yeah, that's much as I can say.
Add to that, VS. I also got to say, Google is culturally not set up to go on the offense as far as law enforcement collaborations to take down abusers goes. I think that's a big difference, I think, that we have to other companies like Microsoft, where they have a very big team which is responsible. Their digital crimes unit, if you've ever heard of that. Microsoft has a very, very big team that deals with that, and Google does not. I regret that, but I don't see that changing anytime soon. The cultural differences are just too big right now.
Sure. Yeah. No, I think, different organizations handle this differently. And I'm sure that if it's sufficiently big, you will refer it to law enforcement and hope for the best. And it seems to me that oftentimes nothing is going to happen. But yeah, I just wanted to know how that gets handled, from your point of view. So cool. More questions?
It's more of a comment than a question. I was pretty fascinated by the randomness thing you mentioned, that math.random was not really random. Just wanted, if you could talk about that again. That was pretty interesting to hear.
Yeah, so actually, without giving away too much information, we have used machine learning to track, uncommon patterns and ad conversions, and found a high correlation between these known campaigns that were doing math random, like using Java methods that were supposed to be math random, and very specific patterns across our conversion heat maps, so that you would actually get predictable shapes based on and now this also relates to another constraint which reduces the randomness of it, which is the screen size, right? First you have to determine the size of the screen so that you can make sure that when you push out a random click, it's going to be within the pixels of where it's displaying the ad and not off screen. So that limits the available options as well, right? In a single ad, you probably only have a few thousand pixels to pick from. And so they try to pick these at random, and then it is very interesting. I mean, I don't think I can even really understand like the mathematical phenomenon that's behind it, but I assume it's because when you call a math random function, it's using actually a deterministic algorithm, right? There is no true randomity in these baked in random classes. So that's where I assume it comes from, in coordination with the other constraints, like the screen size and the size of the creative itself is limited to a very certain size of 100 by 500 pixels or something.
Very cool. More questions, people?
Cool. Thank you so much, everyone. Really appreciate it.
All right. Fantastic. Thanks so much, Arthur. Really appreciate this clear description of what's going on in ad fraud. I mean, obviously, there's a lot for us to learn, but I think this gets us started. Thank you. This is wonderful. So we have about 20 minutes before the next talk, which is by Vadim. Should we just go ahead in 10 if Vadim's here already, or should we wait?
No preference from my side.
I think it's up to Vadim if he's here already.
I can ping him.
Could you repeat the question? I've just plugged in.
Vadim, we're about, we've just wrapped up Arthur's session. And instead of waiting 20 minutes, I was wondering whether we could start in 10. So give people a 10-minute break and start in 10 minutes. Would that work for you?
Absolutely, yeah.
Great, thank you. So let's take a 10-minute break and sync back up at 4:50 p.m. Eastern, 1:50 Pacific. And we'll learn more about Ghidra with Vadim. Excellent. So see everybody in 10.
I've also linked the advertising fraud samples, which Arthur had prepared. So maybe, Arthur, you can spend a minute explaining what's in that zip file.
Yeah, so we have samples of each fraud type I enumerated in the slides, and they all should be labeled. I did actually, once you get the slides, they should, I created a slide specifically to give you direction on what each sample is for. But the sample should have examples of attribution fraud, programmatic clicking using a couple different API calls, and the spoofing of fake iOS apps.
Fantastic. Great. Thank you so much, Arthur. That's super helpful. So we'll sync back up in, I guess, 9 minutes now at 4:50. See everybody shortly. Bye. So welcome back, everybody. And the next speaker is Vadim Kotov from Google, and he's going to be teaching us about JNI and about Ghidra. So over to you, Vadim.
Thank you. Hello again, and welcome to the Introduction to JNI and Analysis with Ghidra. JNI, of course, stands for Java Native Interface. Oh, by the way, is audio still okay? Audio, video?
Yes.
Oh, great.
Awesome, thank you. By now, we saw that Android allows you developing your applications in using many languages and many platforms. And one of the ways to extend Android runtime is to write parts of your app in C or C++ and compile it to the native code. And Java Native Interface is the glue that connects your Java or Kotlin application to your native code, to your native library. There are many use cases for that. For example, it allows relatively hassle-free porting of already existing libraries for other platforms. For example, Unity the game engine is all its core code is implemented in the as a native library. Another use case is perhaps extending functionality of Android runtime. Maybe you would like to efficiently implement some esoteric or obscure encryption algorithm. Or perhaps you would like to implement some, algebraic library and you'd like to code it up in a native code for efficiency purposes. And finally, it is used for packing obfuscation and other adversarial techniques. For example, anti-debugging tricks are very easy to implement in native code, and they might be very powerful. A lot of packing, unpacking, and obfuscation might happen in the native code. Malicious functionality might reside in the native code as well. And of course, malware is using that mostly for adversarial purposes and hiding malicious code. The best information source on the JNI is, of course, Oracle's JNI specification. I think it's very detailed, it's very large, and it describes every aspect of Java native interface you might be interested in. JNI is supported pretty much out of the box in Android Studio. You might want to download NDK, which is called, which stands for Native Development Kit. You can do that through Android Studio's interface. It's also very straightforward. When you create a new project, you scroll down a bit and select native C++. And that would create a Hello World project. It will create your Java entry point, and it will create a a piece of native code that performs a very simple thing. So this example has a text view, and it displays a string, but the string is returned from the native code. The native method in this example is called string from JNI, and it is defined like so. It is a public method, and it should be prefixed with native, so that your application knows that so that your application is aware of the native methods available to it. So another observation is that actually let's direct our attention to the right part, to the C++ part. First of all, the file name is nativelib.cpp, and that will compile to libnative.lib.so. And the first thing that is executed in the Java code is, as you can see, load library, and a string is passed as an argument that says native lib. This is how you can load native libraries to your application. The system will actually understand that this native lib thing should be libnative.lib.so. So it will automatically search for versions of this name with lib prefix and the SO extension. Now, SO stands for shared object, and it's an ELF. It's which stands for, on its turn, stands for executable and linkable format. It's a very common file format on Unix systems. On Linux is a main executable format. Another thing to notice is look at the package name, right? Our package name is com example hello from CPP, and look at the method name in the C++ code. It is Java underscore, and then goes a full path to our class. That is our package name, com example hello from CPP, our class name, main activity, and the function name, or the method name, string from JNI. And dots on the path are replaced with underscores. So this is how your Java part of your app will recognize which method, or rather, yeah, your Java code will recognize which method are you referring to when you're calling it. Okay, what else is interesting here? On the C++ side, you can see that the method string from JNI takes 2 arguments. And here we pass no arguments at all. That's because these 2 arguments are passed implicitly. You don't pass them directly, but they're passed along at some point. First is this pointer of type JNI-env, and we'll talk about it in a minute. It is the Java interface pointer, and it is probably the most crucial thing that is available to a native function in the Android context. And as you can see, this, as we declared here on the Java side, the method should return a string. Well, in this case, the return type is JString. In the native land, string is represented by the type JString. And this is how this value is obtained. See, we define a string, which is a C++ string, but we can't return it because we need the J string. And to the ASCII representation of the string, that's what this C_str does, to a function called newString_UTF, which creates a J string. And notice that this function is accessed through this env, the J9 environment pointer. Okay, yeah, I think we can now talk about the interface pointer. So the aforementioned J9 env. This is what it looks roughly in memory. So it is a pointer. Every thread has its own interface pointer, and it, on its turn, has a number of pointers to interface functions. And these interface functions are essentially helper functions that allow you call Android APIs from the native code. That's how your native code knows how to call Java code. And as we saw this example right here, we call newString_UTF. It's one of those pointers. It exists at some offset relative to env, and we pass it, for example, a string that creates a new Java string. So how does your app, how does an Android app, the Java side of the program, know how to call a particular native method? Where do they live? Well, we've covered one way, that's called runtime discovery. If your function is appropriately named, like so, it's prefixed with Java underscore, then full path to your class, then underscore, then your method name, as shown here in our string from J9 example, then it should have no trouble calling this function. But it is not necessary. You can explicitly register functions in your native code that you would like to expose to Java land. And this snippet here shows how to do that. Let's walk through it. First, we the class with this path. That's the only sort of precondition. And we get the class handle to this class. We will need it a bit later. For now, just take note of it. And then we declare an array of structures called J9 native method. These are, hang on, let me, okay, I apologize. The structure is J9 native method, and it takes, it has three elements. First one is the name of the method. In this case, first one is called native foo. This is the name by which Java side of the app will call it. So in this case, we would have declared it public native string native foo, as shown here. And the second argument is the signature. The signature of a function is a string that simply describes what arguments does it take and what type does it return. In this case, the arguments are in parentheses, and then following the parentheses, the return value. In this case, the parentheses are empty parentheses, which means that it takes no arguments, and V means that it returns void, it doesn't return anything. And then finally, the third element of the structure, J9 native method, is the pointer to the function. In this example, it's called native foo, but it could have been called anything. It could have been called anything. But by the fact that you're declaring that we will see, by using register native function, you will relate this name to this function. let's look at the second line here, second element of the array. It's another function. It's called native bar. Its signature is a bit more complex. Let's parse it. So in parentheses, as I mentioned, there are arguments. And the first one is this very long thing as L, and then the full path to the Java string class, and then ended by a semicolon. So whenever you see L, that means that a fully qualified class name follows. In other words, it's just a simple full class path. Any Java string, if we expanded its full path, it would be java.line.string, except that dots are replaced with forward slashes. That's how class paths are represented internally. And then I means just that the second argument is integer. What is the difference between these L things and just regular single letter types? The difference is that these are atomic types. So integer is an atomic type. It's not a complex class that's made of something. Now it is a class in Java, but is in the context of JNI, it's an atomic type. As opposed to string. A string is usually a sequence of characters, which is an atomic type in itself, but it's a sequence of characters in memory, and that's why we need to specify that full qualifying path. And then the return value is represented by letter Z. What's Z? That Z means Boolean. The same thing. I'm not sure if you can see it, but on the bottom, and you'll get the slides, on the bottom, right below this square with the code, you'll see a link to Oracle's page describing these signatures. And it has all the letters, what they stand for and why. All that information is in there if you're interested. And then finally, you call register natives, and that connects these names to these pointers and makes your app aware of these methods. It takes 3 parameters, 3 arguments. One is the class in which these native methods are called. That's why we needed it. We needed to get the handle to the class right here. Then this array of methods. This array of methods could be defined in function. It could be defined as a global variable. Doesn't matter. And finally, this is the size of this array. We could have just put 2 there because there are 2 elements, but that's not maintainable. This actually calculates the number of elements in an array by taking the full size and dividing it by the size of a single entry. This code is taken from Android developer webpage, so that's how they recommend doing it, and it's a good maintainable way to do that. So to summarize, there are 2 ways your application knows how to call your native methods. One is a runtime discovery, just appropriately name your methods, and 2, register them using register native function. Now, question is, where does this code belong? The register native code, right? Surely there must be some kind of a way to execute it prior to these methods being called within a function. And in fact, there is a function that you can define in your native code that's called JNI onload. This function is called right after you load the library in your Java part of your app. The JNI onload is the first function to be executed, in which you can then register your native methods, and then these native methods will be available to your app. So this slide overall is about entry points to the native code, and JNI onload is one entry point. Another entry point is, of course, properly named methods that are exported using runtime resolution. There is a third way, it's a sneakier way. It's not Android specific, it's specific to ELF. And for more information, you can refer to this brilliant blog post about C startup and specifically init array and Finney array sections. Now, init array is a section in an ELF file, which is essentially a function of pointers. An array of pointers to functions. And these pointers, these functions are executed one after another upon loading your ELF into memory. And this ideally should execute even prior to JNI unload. And this is sometimes used by malware to just sneakily execute code before anything else, and by various commercial obfuscators and packers, also as means to complicate the analysis. So when you're analyzing some code, let me backtrack a bit. As I mentioned earlier, sometimes, especially in Android malware, a lot of conventional code that you'd see in Java would be deliberately implemented in C++ or C. And it is important to know what are the difference between two equivalent pieces of code, one in Java, another in C++, using JNI. And here's an example that we saw earlier today. It's a very short snippet that simply takes calls getSim operator. The 2 lines of code. One is we instantiate the telephony manager, and then we call getSim operator. Very straightforward. But that grows quite a bit if you want to do the same thing in your C++ code. First thing to do is you need to get a handle to the context class, because getSystemService is a method of context class. So you get a handle to the class, then you need to get the method ID for the method getSystemService. And to do that, you have another helper function called getMethodID, which takes 3 arguments. One is the context class. That's why we needed it. And we pass it because it exists under the context class. And then the name of the method, which is getSystemService, and then the signature. In this case, it takes a string. So Android Studio provides you with all these nice constants, such as this telephony service, but it's really just a string. So it takes a string as an argument, and it returns an object. How come it returns an object? Because as here we see it returns a specific class, telephony manager. Well, all the complex classes in native code are represented by just object as far as the signature goes, and at the just as at the level of C code represented by J object. So essentially, we're requesting an ID of a method called getSystemService with this signature. Why do we need provided a signature? The answer is because of method overloading. As you know, Java is an object-oriented language, and Java platforms such as platforms based on Java, such as Android, of course, also follow this sort of object-oriented design. And I'm not sure if there are other versions of getSystemService, but just in case that you have multiple methods with the same name but different arguments or return values, you must specify the signature to that method, signature of that method. Okay, so we have the system service ID. Now we can actually get handle to the telephony object. We're arriving at the end of this method, of this first line of Java code. To do that, we call call object method, and it takes the actual context. It gets the method ID, and it gets the arguments. In this case, there's only one argument, that is this argument. Again, is just a syntactic sugar provided by Android. It's really just Android Studio. It's just a string called phone, which must be a Java string, by the way. So we used new string UTF, a function that we're already familiar with. And this is how we get this object called telephony. And as you can see, it is JObject, as opposed to telephony manager. And notice that all these helper methods, they are accessed through, and that's our Java interface pointer. That's why it is so important. Okay, and that concludes the first line of this Java code. And the second line, essentially same idea. We get a handle to telephony class because we're going to get its method ID for getSim operator. We resolve getSim operator, and then finally at the end we just call object method and pass it the class and pass it the arguments. So quite a bit longer, but it is important to know how these things look like in native code in order to recognize them during the analysis. Of course, everything is well documented in everything was well documented on the Oracle's webpage about JNI. Moving further. Okay, so we've now have some basic knowledge of JNI, and now it's time to get familiar with Ghidra interface. So you can, if you'd like, you can follow me. This is our project in Android Studio. It's the Hello from C++ that we saw a few slides earlier. This is Ghidra. When you open it, we have this window. That's a project view. We create new project. Ghidra supports shared projects. In this case, it's going to be a non-shared project. And we just give it some name. I don't know, it's called GNI projects. Finish. So that is your, you created your project. You then import your binaries to your project. You do import. And in this case, we're going to load this libnative SO. The only thing is I'm not sure if this is exactly the method we want, but that's fine. It's the exact binary I wanted to show you. Oh, that's fine. For those who don't know, Ghidra is a reverse engineering framework. It's mostly used for analyzing native code. I think it supports some bytecode, but mostly for native code. Supports a multitude of architectures. Most of by the way, the code compiled as a part of the C++ project in Android Studio is typically compiled in four architectures. One is ARM 32, then ARM 64, then x86 32-bit, and then x86 64-bit. But the majority of devices these days, I believe it's safe to say that the majority of devices are 32-bit ARM devices. And malware is usually not as charitable as Android Studio. They will only include the bare minimum. They will only probably include the 32-bit ARM library. And that serves two purposes. One, it keeps your files smaller. And two, if you ever want to run it in Android Studio emulator, which is by default x86, because desktop computers are x86, this app, of course, won't run because it won't have the necessary libraries. And that is sort of a anti-dynamic analysis trick that you get for free by not including anything other than 32-bit ARM library. But now we've imported this library here, and we just double-click on it, and it will pop us a window that says we have not analyzed it yet. would we like to do it now? And yes, we do. These are analysis options. You can read about them later, but just leaving them by default works most of the time. It works fine. And is the main Ghidra interface. So what you're seeing might be slightly different from what I've seen because I've done a couple tweaks, but it should be 90% the same. These are two main windows. This window right here, I don't know what is this square. Okay, it's gone. This window right here, big window, is a disassembly view. So it says listing, and this is the decompiler view. This is actually not that much of a disassembly view. It has all the disassembled code, but it also has all the data, all the structures. And right now we are right at the ELF header, and that's why decompiler doesn't display anything. It's not code. These are some windows. This one has sections of ELF. We're not going to preoccupy ourselves with this window right now. And this one on the bottom is data types. You can specify your own data types and thus make the disassembled and decompiled code a little bit more comprehensive, but we won't touch on that today. What is of great interest is this thing. This window is called symbol tree, and a symbol tree contains information about all the functions, about the functions that are imported, the functions that are exported, and so on. This is a SO, a shared object. A similar concept on Windows is dynamic link library. So it's not a standalone executable, it's just a library that is meant to be loaded by other programs. This library depends on other libraries. That's what the imports section is for. It just declares what does it depend on, and you can see these are the functions that it depends on. For example, strcmp, smprintf, these are libc functions, very well-known libc functions. Now, since it is a shared sort of library, it also makes some of its function available to be called by a program that uses it. And in this case, that would be our Java program, our Java app. And there's a list of all the exported functions. You see, it's quite a big list because it implicitly creates most of them. This is just a list of all the functions from C++ classes that it recognized, and the namespaces, all the C++ namespaces. Functions or exports is the most interesting thing for us because we know that that's a Android shared library. If it is Android shared library, then it must export some of its functions. As you can see, that's a big list. So searching for stuff in it just by looking will be counterproductive. Luckily, we have this search bar. And we know that there are two major entry points into native code. One is dynamic resolution, which starts with Java _. As I suspected, this is a slightly different library. It has two exported methods, but the one that we shared will probably only contain one. This one, string from JNI, the one we saw. Nonetheless, doing it like this automatically shows you these methods, these functions that you might be interested in. So let's go to, oh, actually, I'm sorry, the sim operator is a very relevant method too, because we just saw how getting string operator looks in C++. So that's right there. Okay. Anyways, string from JNI. Let's quickly get back here and recollect what our C++ code looks like. Not much really, just 2 lines, creating a string and then calling new string UTF and hello C string, getting the C string of C++ string. Let's look at what it looks like here. So we jumped at that function. We just double click on it. The disassembly view scrolled to this function. Here's the assembly code, and this is the decompiled code. An important remark about the Ghidra decompiler is that it's not a traditional decompiler. Think of it as a sort of a C-like pseudocode. The way it works off it takes a CPU specification, in this case, it's ARM 32-bit CPU, and lifts it into this pseudocode. So if you have a CPU that is not supported by Ghidra, Ghidra allows you adding this CPU by adding the CPU specification, and it will be automatically exposed to the decompiler, and then the decompiler will lift whatever CPU you extended the Ghidra with. It will be able to decompile it. That makes it very, let's say, universal. It's a very retargetable approach to decompiling code. But of course, it's not as great as a custom decompiler for C++ code. So just keep that in mind. It's not that something wrong with the decompiler, as you might see some people complain, but it's just the fact that it's not a decompiler in a traditional sense. And our two lines of code in C++ here look quite a bit different. They look like many lines of this pseudocode. But in reality, all they do is simply make some of the implicit stuff explicit. Because what this here does, from the programmer's point of view, this line, std string hello equals hello from C++, from the programmer's perspective, of course, it's just as simple as just writing this simple one line of code. But what happens under the hood is, well, std string is a class, so which means it must be instantiated. Probably its constructor is called, probably some memory allocated to contain the contents of this object, and then this argument is passed to the constructor, and then the handle to that object, a pointer to that object, is available to the rest of the code. So that's exactly what we see here. This is a constructor for the class basic string, which is what basic string is a class, and that is the constructor it is called. And then this is where this variable here is the pointer to your string. And as you can see later on, this is the destructor. Once you've done with your, once the code is done with that object, it should deallocate it. So this stuff exists implicitly in the code, and that's why often what you see in the C++ code is quite different from what you see in the decompiled code. Another thing is that you might notice this conditional statement here. Where did that come from? And this is a very common code pattern that you'll see all over the place in native code. This is so-called stack cookie or stack canary. This is a way compilers check whether a buffer overflow occurred or not in this case. So if no buffer overflow occurred, it will just return. But if the stack canary is not equal to its original value, then it concludes that there's been buffer overflow on the stack, and this function is called, and this function actually shuts down the application, so it never returns. So just bear in mind that there are a lot of implicit stuff that happens in the native code, and always focus on just these familiar things. And so this is a Ghidra interface. I'm going to close this. I'm going to save it. I'm going to close it. I'm going to import another file. By the way, you can either do file import or you just press I. Another one. So this is a native library that is shipped with another piece of malware. It's also toll fraud. Toll fraud, all my examples will be toll fraud, by the way, because toll fraud deploys so many various tricks, obfuscation, native code obfuscation, packing, and whatnot. So it's just really, really nice malware category to showcase some of the aspects of these analyses. Same thing, we loaded the file. Let's look for our exported Java methods, and we have quite a bit here. I will open this one. And you might notice that it's all messed up, as you can't make a whole lot of it. What is this, for example? This first argument is integer, pointed to an integer. Well, we know that it should be JNIM. So these are these offsets to those functions in. So param1 is our environment pointer, and these are attempts to essentially access it. What is this method, for example, of the offset of, what is this function, the offset of OX18? We don't know. And sometimes Ghidra won't properly understand the types. And in fact, Ghidra by default is unaware of these types. It's in the previous example, everything seemed normal, but it seemed normal because it was a clean developed, a clean executable that we've just compiled in Android Studio. This one was stripped. Most of the information about types is gone, and we're going to need to help Ghidra to understand that. Which brings us to another part of another section of this presentation, is how to make Ghidra aware of types used in JNI code. Here's the same example, but slightly smaller. So we know that this first argument must be JNI, and so we could retype it. And that points, we know that these point to some JNI helper functions. Remember, these points are just simply points to intersection. They exist at various offsets. Well, to do that, we need to get hold of H header file that contains info about types, and we go to file, C source, and add our JNIH. Ghidra shows us this is the dialog that you'll see when you do that, and this window are the flags of the GCC. The GCC is a C compiler that are used to parse this header file. And then I'm not sure if you can see this. It's the button says parse to program, and this is how you make Ghidra aware of any C header file, any C. In fact, not only header, any C file. It will just read types and definitions from there. Where do you get JNI? If you have Android Studio, it's probably already there somewhere. Just search for jni.h. Or otherwise, you can just go to Android source code repository. Android is open source. You can just go to the code repository and download it there. And the next part is a bit subtle. What I would recommend to do is trying to pre-compile it with these GCC flags. I omitted most of the flags here, but you just go to your command line, invoke GCC, and you can see what it outputs. Why do we need that? Why this step? The answer is, unfortunately, most of the time when you just import something random, such as jni.h, it won't load it. It will tell you that some error occurred, and unfortunately, it won't provide you a lot of error information for you to debug. So doing this allows you to collect the error information from the compiler and get a better idea of what might be wrong with the code. The problem is that even if you successfully pre-compiled your header, what will happen is it doesn't mean that Ghidra will understand it. So Ghidra is a bit more capricious than GCC itself. So sometimes you actually might just do some trial and error. But in this case, oh, by the way, JNIH is in the archive that we share with you, and to how this was done, so that if you ever need to load your own header file and run into problems like this, you know what to do. So let's look at this output. There are two things. One is the warning that STDC was redefined. I don't know what that is. I don't know why is it there. And another is that it doesn't like the VA list type. What is VA list type? There are functions in C and C++ that have a variable number of arguments, and they may be represented by this type called VA list. So to understand what's going on here, I'm going to need to go over these flags, specifically this one, d_stdc, and this one, d built-in VA list void, and understand what do they mean. See, this d is equivalent to a C macro that defines a variable. That defines essentially a macro, either a macro variable or macro function. In this case, it introduces a macro variable called stdc and sets it to 1. That's what this flag does. But I think JNIH already does that. So that's where this double definition error comes from. Then this one is equivalent to define VA list as void. So that's why it says, hey, that must be void. But it can't be VA list. How to solve this problem? There are two ways. One is you play around with flags and make sure that all the dependencies are satisfied. This JNIH, all that I comment out, it's actually dependent on other health, and Ghidra must have those to be in a source file. So it actually get really complicated with these nested dependencies. What we're going to do is, I've never done that, this first method, but that's probably the right way to do it. But we're going to hack your way in a way that works that very well. Well, depend on any external. That's what will make Ghidra happy. And this is how we modify the JNIH. So this is how we modify JNIH. We comment out these dependencies. We don't need them. We explicitly define some of the integers that it is using. Effectively, we mocking std header that contains number of integers. Standing defines the list structure, effectively mocking the str. So now all types H are accounted for. You're happy. Now it was to fix this issue that we saw, that we the types that we saw, and should read. Hopefully, this is what we should see.
Hey, Bill, did we lose both? Oh, there's Vadim back.
Yeah.
I feel we lost.
I'm not sure. I'm not sure.
Okay, you're back, Vadim. I'm not sure what's happening either. But we somehow lost both you and Sebastian.
I intentionally restarted.
Oh, there you are. Okay.
So I reconnected my internet. Hopefully it might work. So with luck, we will get our wrong types, we recognize our types, and all the offsets to Java's pointer successfully resolved. So let's go to our code. So we go file, we go our C source, we press this plus button to add this JNI. We do it. We pass them. Yes, and yes. And that's brilliant. Now we like to turn that into J and the pointer to JN, and we return variable JNI, and it already pops up this helper dialog, which is a drop down, which is a sign. That's what we need. It's a point. Now these I might disconnect. I think I'm still in. Can you hear me? Hello?
Hey, Vadim, you're breaking up fairly significantly now.
Yep.
How many minutes do you have left?
Can you hear me?
I can hear you.
Ellie.
Yeah.
Okay. I think Vadim is breaking up a lot right now.
Yeah, Vadim is breaking up a lot.
You know, one possibility, maybe
right now.
We're also close to the end, right?
Maybe he could connect to audio from his phone.
Yeah, that may be a possibility, or okay.
But if so, we cannot see his share screen, right?
Yeah.
No, you can. you can actually connect to Zoom and just defer
Share
to
your
audio
video.
via phone. Yeah.
You can do that. But another possibility, I don't know, Sebastian, if you have the slides that Vadim is using, you know, you could share it, and if you have it, and Vadim can talk through the slides using just an audio channel.
Yeah, we can probably do that. Let me check.
Okay. So what I'll do is I'll go off video as well and see if
I'll present now.
okay, here we are. And,
Vadim, what slide were we on? I remember this slide, for example. Vadim, can you hear me?
Vadim? Let's see if he's still on.
I fear we lost Vadim.
Yeah, I fear we did.
He just texted us that he thinks there's an internet outage in his area, which can definitely happen. Well, let's see if I'll just give me 5 minutes, but I can also try to walk through the slides. I think, and that's going to be interesting because the first time I'm seeing these slides. But I'll give it a shot. So we were here, and we said, okay, there's some problems with compiling that stuff, and we can do the hacky way or not so hacky way. And for this particular session, we're going to do the hacky way, adding a couple of type defs just to get the header self-sufficient and get it to compile.
Hey, Sebastian, I see that Vadim is back on.
Oh, okay.
I don't know if he can speak or hear me yet. Vadim, are you back? All right, well, maybe you should continue and Vadim can chime in when he's ready.
So here Vadim has created like, what does that hacky fix look like?
Yeah, I'm back on. I'm not sure for how long. Yeah, me, folks?
We can hear you.
Yeah.
Can you hear me?
Vadim, Sebastian is showing your slides from his screen. So if you think that'll help any bandwidth issues at your end, you could have him present and you speak.
Can you hear me?
Yeah, not great, but we can.
Folks, how's the audio?
Yeah, start talking.
Yeah. Oops.
Well, that's I'm gonna.
Maybe you should keep going, Sebastian, because I think it's clear that bandwidth issues at Vadim's end.
I attribute to the California virus.
I can imagine it's a tough situation you guys are all in.
Okay, I'll just text him. I'll finish his talk. And here he has provided like just how to create that hacky fix, get rid of the standard C headers, explicitly define your integer types that are going to be used, and then create this type def struct for this one type that is actually needed. And then you can compile the headers so that you can import them into Ghidra. So you can import into Ghidra, and I'm sure Vadim actually wanted to show you how to do that. But there's this data type chooser dialog where the headers that you have compiled are now going to be available. And that makes it very easy then to use these data structures as part of JNI and it makes it very easy to understand which is the class name, or which is the method name, or what is the arguments. And that's what it looks like. So right on top we have the original code, which Vadim has showed live a couple of minutes ago. And on the bottom, it's what it looks like after you have defined that data structure with all the method pointers that now have names instead of just being parent1 plus OX18. Now it's find class, and you have a new string, and you have get method ID, and so on. And that just makes it very convenient. I would say nearly Java-like to read. And so you have, oh yeah, we do have find class Java lang string. We're creating a new string GB2312, and then we are calling the get method. The get bytes method on that string. So we return a string into a byte array, and now we can read it, the decompiled C code, nearly as well as the Java code that we have. That's already it. Actually, there's a couple of useful links. The first one, the official site has a couple of very useful courses. There's a book written by Chris Eagle and Carol Nance, published by No Starch Press. I gotta say, Chris Eagle also wrote an interesting IDA Pro book, and so he now just recently published that Ghidra book. I haven't read the Ghidra book, but if it's as good and comprehensive as the IDA Pro book, then I would definitely recommend that. And the last one is a nice tutorial emulating Ghidra's P code. Ghidra's P code is essentially the underlying bytecode that powers Ghidra's disassembler/decompiler engine. So check it out by a guy named John Totahi. And that was it. If there are any questions, I hope that Vadim is going to be back, because I can barely answer any questions, but we can give it a shot.
Awesome. Thank you, Sebastian, for jumping in and saving the day. So, and I see Vadim on my screen. I don't know if he can speak or not, but let's throw open the floor for questions.
It seems like my connection is stabilized right now. Can you hear me, folks?
Very well, actually. Yeah.
Oh, fantastic. Yeah, we have outages, unfortunately, in the area from time to time. I apologize for that.
No worries at all. Thank you for your excellent presentation, Vadim. So let's go to questions from the audience.
Vadim also has prepared a couple of samples. I pasted a link in the chat room. Vadim, you can also talk a little bit about what people can expect in that sample pack.
Oh yes, let me share my screen real quick. So I caught the end of the presentation, so that's a really good. It's a really good. Was a really good ending to what I was actually going to say. Goodness, how do I? Let me stop sharing for now. And yeah, so that's where we stopped, and that's fine. We know how to resolve the methods. But I would like to show you the contents of the files that we shared. It's right here. So here there's hello from CPAP. The source code for is in it's on slides, and this is actually essentially a default project that Android Studio creates when you create a new C++ project. JNIH it's already fixed. JNIH that you can load into your Ghidra project and use. And this one, the DC API one, is the last sample I showed you. It's an interesting sample. You can check it out. It's frontal fraud. It's not really crucial for this session, but this one is a full APK. It's another Joker instance that's using a native library to hide some of its malicious code. And this this was meant for the sort of the either lab session or analyzing in your own time. The only the only hint that is required for this one is that it is using this method. It explicitly registers the exported methods. And so to find this code, you actually need to search for JNI onload in this search bar right here. In this sample, of course, it is absent, but it will be present in that piece of code. Additionally, we're going to probably look at that sample a bit closer tomorrow too, for a different reason, because it also uses some obfuscation techniques. That's the contents of the archive.
Great, thank
that's
you.
all from my side.
Thank you, Vadim.
Be happy to answer any questions.
Fantastic. Thank you, Vadim. Great talk, despite technical glitches. But let me throw open the floor for questions from the participants. Guys, I know it's late in the evening, but go for it. All right, so, with my machine learning background, I'm sensing that 6 p.m. Eastern time, after several hours of lectures, people are kind of wiped out. This is what happened yesterday, what happened today. That's a small n to base any conclusions on, but I think it looks like people are sort of wiped out. So, guys, do you have questions general questions about the day as a whole, given that we have the lab coming up now?
I was sort of thinking of have you tried binary ninja at all? Like, do you have any so among the three prominently used ones, Ghidra, IDA, and binary ninja, do you think that Ghidra performs particularly better at this, or was it just a preference?
That's a good question. The three of them are all good tools. I unfortunately have not used a binary ninja for a few years now. I used it early on. It since then acquired many features that were absent when I was using it. So I'm pretty sure it's more or less on par with other reverse engineering frameworks. What stands out about Ghidra is that it is, first of all, open source and free and openly available. Its disassembly quality is great. Their decompiler is, I would say, pretty helpful and definitely very interesting. It's a very interesting approach in this sort of this retargetable lifting code into C-like pseudocode. And it is also brilliantly documented. Just go on the official website, and whatever your questions you might have about Ghidra's inner workings or about how to use Ghidra, you'll find it there. And so that's why I think it's a tool that's worth, you should give it a try.
Fantastic. Thanks, Vadim. Questions from others?
This is more of a clarification. So the overall approach that you took today, was it to first use something like JADX to look at what JNI files are even needed, and then try and disassemble them using Ghidra, so that you have like in the APK you have a set of Java classes as well as a set of SO files?
Correct. The starting point is always the Java code because that's the entry point for Android apps. We will note during the analysis, you notice that some of the methods are defined as native. And so that gives you an idea that, oh, yeah, I need to go check the native library.
Mm-hmm, mm-hmm. Yeah, thanks. Yeah, that makes sense.
Everyone else, folks, more questions, discussion? All right. What about questions and discussions in general with not specifically focused on Vadim's most recent talk on JNI and Ghidra, but on malware analysis in general as covered during the rest of the day today?
My thing was pretty good. I followed through most of it, I feel. Some of the stuff I feel like once I actually get my hands dirty, I'll have more questions, I guess.
Thank you, Samid. I figured that might be the sentiment of some people, especially as, you know, these are relatively long days and we're going through a lot of material. So I think some people at least don't have the comfort level yet with everything to ask the detailed questions that will undoubtedly pop up once they start playing around with the code.
Right. So yeah, if you get a chance to take a look at the samples that we shared throughout the day, and you have any questions tomorrow during lunch break, yeah, we'd be happy to chat about those. Or if you had any trouble with any of the tools.
Yeah, thank you. Sorry, go ahead.
I have a quick question. I mean, during your daily life for the Google Fox, I mean, I guess maybe some of you maybe spend a lot of time on the source code and reverse engineering, right? I just wondering, I mean, what kind of, conditions you will look into the specific apps, and maybe for other conditions you may just, say it's a virus, it's a malware, and then just go and just let it go. So do you have any, experience to share?
Is the question about like how deep do we dig when we believe something is suspicious?
I think it is, Sebastian.
That's a really good question. In general, I like to think about the level of effort that we should put into malware reverse engineering as a bimodal curve of like two peaks. Either we spend very little time on it and we just move on, or we spend a lot of time on it and we get a lot of lessons from it. The worst case is, and that should be avoided, is you spend a lot of time on something that you don't learn anything from, because that's just wasted effort. And so I would encourage, or I do encourage people on a regular basis that try to get a lot of the malware reviews done in less than 5 minutes, ideally in less than 2 minutes. Most of the mass malware, in particular, when we can fall back and use our own internal tools, actually very quickly to analyze, and you're very quick to see what's going wrong. You know, oh yeah, this is clearly toll fraud, or it's clearly whatever. And don't think too much about these. There's a never-ending supply of easy to classify and analyze malware samples out there, and there's nothing really to learn from those. So get that down under 5 minutes per sample. For the very, very interesting samples that are maybe discussed in the tech press among security researchers, or just internally, let's say the Triadas of the world, the Ghost Pushs of the world, and so on. We spend a lot of time on those. We create many, many pages of reports about all kinds of aspects. These are very long-lived campaigns that keep innovating themselves, right? And they are just very successful at what they're doing. And so we spend a lot of time on those and a lot of different people on those. We literally, for Triada, we've probably created, wouldn't be surprised if it exceeds 100 pages of documentation actually over the years. So spend a lot of that, try to learn a lot, try to learn how to improve the system, try to learn how to, by system I mean Android itself, try to see how you can improve Google Play policies, try to see how you can improve the detection and so on. So those are the two extremes. What you want to avoid is looking at a sample for like an hour, 2 hours, maybe even a day, but never actually learning anything from it that can make the situation better in the long term, because that just slows you down. So I would encourage everybody looking at samples, at least internally, make a decision what you want to do and make that decision fast. Is it going to be a typical sample that you can look through in 5 minutes, set a flag to protect users and move on? Or is it something that needs a deeper investigation? Then start talking about it, start getting other people involved, and turn it into a real project.
Thanks, Sebastian. Any more questions? All right, so it sounds to me, the silence sounds to me like people are, you know, somewhat wiped out. So like yesterday, I think we'll wind down for the day now. And I did want to announce one change tomorrow to the schedule. Tomorrow there actually was no scheduled lunch break because I had taken it up to talk about Android malware research at Dartmouth. But I think what I'll do is I'll skip that. And so we will take a lunch break as usual tomorrow at 3 p.m. Eastern, 12 noon Pacific, so that people can ask questions as they did to some extent this afternoon. So with that, I'd like to thank all the speakers today. JJ, Arthur, Vadim, thank you both. Thank you all three for you know, great talks, and also thank you to Sebastian for, you know, pitching in sort of on the spot as needed towards the end of the day today. And we all look forward to seeing you tomorrow. So thanks so much.
Thank you very much, everybody, in particular, of course, the speakers, but also the attendees who've made it through the second day. Really appreciate that. And I'm looking forward to see you again tomorrow. I think it's really nice to see the level of engagement that people stay connected to this call and just take the full 6-7 hours.
And there are people on this call who've been, you know, at least 2 students are from India who've been, at least one of whom was around till about 15-20 minutes ago. So, and that's about, you know, 3:30 a.m. there. So
yeah, that's very impressive. And we're very grateful for those folks who stay around so long.
Well, we're grateful to you guys for teaching us so much about Android. So let's sign off for today and see you all tomorrow. Good night.
Bye, folks. Have a
Bye,
nice
and thank you.